Welcome to the mechanics of rest. Most of the planets that have ever existed are dead, not dormant, not waiting, dead. Their atmospheres stripped away, their surfaces baked or frozen past any chemistry that could sustain complexity. Their oceans either boiled off into space or locked beneath kilometers of permanent ice. The universe has been forming worlds for nearly 14 billion years, and the overwhelming majority of what it has produced are ruins. We know this not because we have visited them, but because we have learned to read them. The rocks of Mars carry a chemical record of water that no longer flows. The atmosphere of Venus holds the signature of a runaway process that may have erased billions of years of more moderate conditions. The moons of the outer solar system preserve, in their ice and their interior heat, the outline of what liquid water requires to persist. And the silence of the cosmos, the fact that in 60 years of listening, we have heard nothing that sounds like anyone, suggests that whatever filter separates a formed world from a living one is either rare to pass or catastrophic to fail. If you find these journeys worth taking, a like and a subscription keep them coming. New episodes every week, always long, always patient. What follows is an inventory of failure and of the narrow, specific, sometimes improbable conditions that prevented Earth from joining it. Chapter 1: The ordinary violence of formation. The solar system did not begin as a place. It began as a condition, a slowly rotating cloud of hydrogen, helium, and trace quantities of heavier elements, the scattered debris of stars that had already lived and died before the Sun existed. Roughly 4.568 billion years ago, something disturbed the cloud. The leading candidate is a nearby supernova, its shock wave compressing a region of the cloud past the threshold at which gravity could take over. What followed was not an explosion, but a collapse, slow by any human measure, spanning millions of years, the cloud flattening into a disk as it rotated, the center growing dense and hot until nuclear fusion ignited and the Sun switched on. What remained in the disk around it was the raw material of every world in this solar system, and the process by which that material became worlds was neither clean nor gentle nor guaranteed. The man who did the most to place that process on mathematical footing was a Soviet astronomer named Viktor Safronov, working at the Sternberg Astronomical Institute in Moscow through the 1950s and 1960s. Safronov developed what became the foundational theory of planetary accretion, the mechanism by which dust grains in a protoplanetary disk aggregate into pebbles, pebbles into boulders, boulders into planetesimals, and planetesimals into planetary embryos through successive collisions and gravitational attraction. His 1969 monograph, translated into English in 1972, introduced the framework that every subsequent model of planet formation has built upon or argued with. Safronov worked largely in isolation from Western planetary science during the Cold War, and when his work finally reached a broader audience, it was received with the particular surprise that accompanies the discovery that a foundational problem has already been solved, carefully and completely, somewhere else. The picture Safronov assembled is one of accumulation over time, not the dramatic collision of large bodies, at least not initially, but the patient gathering of small ones. A dust grain settles onto another dust grain. Static electricity holds them together long enough for more grains to arrive. The aggregate grows until its own gravity begins to matter, at which point growth accelerates. Larger bodies attract more material, sweep wider paths through the disk, and grow faster than smaller ones. This process, called runaway accretion, produces a relatively small number of large planetary embryos from an initial population of trillions of small bodies, and it does so over timescales of roughly 1 to 10 million years. The terrestrial planets, Mercury, Venus, Earth, Mars, required something closer to 100 million years to reach their final masses, through a subsequent phase of giant impacts among the embryos that runaway accretion had produced. Those giant impacts were genuinely large. The event that produced the Moon, now understood to have been a collision between the proto-Earth and a Mars-sized body called Theia, roughly 4.5 billion years ago, was an impact energetic enough to melt the outer layers of both worlds, vaporize rock on a global scale, and eject enough material into orbit to coalesce into a satellite within perhaps 1,000 years. The Earth that existed before Theia arrived and the Earth that existed afterward were not the same planet. The collision reset the surface, altered the composition of the mantle, and left behind a moon whose gravitational influence would later prove consequential for the stability of Earth's axial tilt. Formation, in this sense, was not something that happened to the planet. It was something the planet survived, incompletely, and was changed by. Harold Urey, the chemist who shared the 1934 Nobel Prize for discovering deuterium and later turned his attention to the chemistry of the early solar system, understood before most of his contemporaries that planet formation was fundamentally a chemical process as well as a physical one. The composition of a world depended on where in the disk it formed. The temperature gradient of the early solar system determined which compounds could condense at which distances from the Sun, producing rocky, metal-rich planets in the inner system and ice-rich bodies in the outer system. Urey's work on the chemical composition of meteorites as a proxy for the early solar system's building blocks established the chemical baseline against which planetary compositions are still measured. The carbonaceous chondrites, a class of primitive meteorites that have changed little since the solar system's formation, carry in their mineral structure a record of the conditions under which the disk existed. And Urey recognized that reading them carefully was a way of reconstructing a world that no longer existed anywhere but in those stones. For decades after Safronov and Urey, the solar system's architecture was treated as essentially fixed, the product of a formation process that, while violent in detail, had produced a stable arrangement that had persisted for 4.5 billion years. This assumption turned out to be wrong, and the people who demonstrated it wrong did so accidentally. In 2005, a team of planetary scientists, Cleomenes Siganis, Rodney Gomes, Alessandro Morbidelli, and Harold Levison, published a paper in Nature describing a new dynamical model of the solar system's early evolution. The model, which became known as the Nice model after the city in France where the collaboration was centered, began from a different initial configuration than the one we observe today. Jupiter and Saturn closer together, Uranus and Neptune closer to the Sun, and a massive disk of small, icy bodies beyond them. When Siganis and his colleagues ran their simulations forward in time, they found that gravitational interactions among the giant planets eventually drove an instability. Jupiter and Saturn reached a resonance that caused Saturn to move outward, which perturbed Uranus and Neptune into wider orbits, which in turn disrupted the outer disk and sent a torrent of material flying inward through the solar system. What made the Nice model striking was not the mechanism, but the result. When Morbidelli looked at what their simulation produced, he found that it matched the actual solar system with an accuracy no previous model had achieved. The current orbital configurations of the giant planets, the structure of the Kuiper belt, the distribution of Trojan asteroids. The team had not set out to reproduce the solar system. They had set out to understand a specific dynamical problem, and the solar system had emerged from their mathematics as though confirming it. The delay built into the model, roughly 700 million years between the solar system's formation and the onset of giant planet instability, also provided a natural explanation for the late heavy bombardment, a period of intense impact cratering recorded in the lunar surface between approximately 4.1 and 3.8 billion years ago, when the inner planets were struck repeatedly by material dislodged from the outer solar system. The Grand Tack hypothesis, developed by Kevin Walsh and colleagues and published in 2011, added another chapter to this revision. It proposed that Jupiter did not form in its current orbit, but migrated significantly inward, toward the inner solar system, before being pulled back outward by Saturn's gravity, in a trajectory that resembles the tack of a sailing vessel changing direction. Jupiter's inward migration would have swept through the region where the asteroid belt now sits, depleting it of material and explaining why the asteroid belt is so much less massive than models of disk formation would predict. Mars's small size, roughly a tenth of Earth's mass, despite forming in a region of the disk that should have produced a larger planet, also fits naturally into the Grand Tack scenario. Jupiter's passage through that region starved Mars of the material it would otherwise have accumulated. What the NICE model and the Grand Tack together describe is a solar system that was rearranged. The planets did not form in their current positions and remain there. They migrated, interacted, destabilized each other's orbits, and settled into the configuration we observe only after a period of dynamical violence that lasted hundreds of millions of years and reshaped every world in the system. The surfaces of the inner planets were bombarded by material from the outer solar system. Water and organic molecules arrived on Earth through this bombardment. The very chemistry that made life possible here may have been delivered from beyond the frost line, flung inward by the gravitational wake of migrating giants. This history matters for the question of dead worlds because it establishes formation itself as a filter. A planet must survive its own construction. It must accumulate enough mass to hold an atmosphere against the thermal energy of formation and the radiation of a young star. It must end up in an orbit that its star's habitable zone will eventually include. It must not be ejected from the system entirely, a fate that may await a significant fraction of planets that form in multi-planet systems where gravitational interactions are strong. A planet must receive enough volatile material, water, carbon compounds, to have the chemistry that life requires, without receiving so much that it becomes a water world too deep for the geological cycling that regulates long-term climate. The formation process is neither designed to produce habitable worlds nor designed to prevent them. It simply operates, and habitability is an outcome that either follows or does not. Most of the time, it does not. The inner solar system produced 4 terrestrial planets, of which one currently supports life. One is a pressure-cooked ruin. One is a desiccated remnant of something that may once have been more hospitable, and one is a heavily cratered world too small and too close to the sun to have retained much of anything. Formation gave each of them a start. What happened afterward is a different set of mechanisms, and the first of those mechanisms is one that most planets cannot survive without a specific and somewhat unusual piece of internal machinery. Chapter 2. What a magnetic field is worth. There is a number that describes Mars's atmosphere, and it is worth sitting with before anything else. The atmospheric pressure at the Martian surface averages approximately 0.636 kilopascals, roughly 0.6% of the pressure at Earth's sea level. A human standing on the Martian surface without a pressure suit would not simply find the air unbreathable. The pressure would be so far below the threshold at which water remains liquid in human tissue that the physiological consequences would be immediate and total. But the number's significance is not primarily medical. It is geological and historical. Mars once had more atmosphere than this. The chemical evidence is unambiguous, and the question of where it went leads directly to the machinery that Earth has and Mars lost. roughly 4 billion years ago, and has not had since. That machinery is a global magnetic field generated by the circulation of electrically conducting fluid in a planet's outer core. Earth's field is produced by convective motion in its liquid iron outer core, driven by the slow cooling of the planet's interior and the crystallization of iron at the inner core boundary, a process that releases latent heat and drives the circulation that sustains the dynamo. The field extends tens of thousands of kilometers into space, deflecting the continuous stream of charged particles that flows outward from the Sun, diverting most of them around the planet rather than into its upper atmosphere. It is not a wall, it is a diversion, a vast asymmetric structure, compressed on the sunward side and drawn out into a long tail on the night side. Perpetually reshaped by the solar wind, it is deflecting, but perpetually re-established by the dynamo running beneath the surface. The physics connecting that field to atmospheric retention was not fully assembled until the 20th century, and the key piece came from an unlikely direction. In 1958, a young physicist at the University of Chicago named Eugene Parker submitted a paper to the Astrophysical Journal proposing that the Sun continuously emits a supersonic stream of charged particles, electrons and protons, flowing outward through the entire solar system. Parker called it the solar wind. The paper was initially rejected. 2 reviewers found the proposal physically implausible. One suggested the author simply did not understand the relevant physics. The journal's editor, Subramanian Chandrasekhar, overruled the reviewers and published it anyway. Within 4 years, NASA's Mariner 2 spacecraft, en route to Venus in 1962, directly measured the solar wind and confirmed Parker's prediction in every significant respect. Parker was 26 years old when he submitted the paper, and the phenomenon he described turned out to be one of the most consequential in the long-term evolution of planetary atmospheres throughout the solar system. What the solar wind does to an unprotected atmosphere is not a single dramatic event, but a continuous, patient erosion. Charged particles traveling at speeds between 300 and 800 kilometers per second interact with the upper layers of an unshielded atmosphere through several mechanisms. Direct sputtering, in which solar wind ions transfer momentum to atmospheric molecules and kick them into escape trajectories. Photoionization, in which ultraviolet radiation from the Sun strips electrons from atmospheric molecules and allows the solar wind's electric fields to accelerate the resulting ions away from the planet. And polar outflow, in which the geometry of a weak or absent magnetic field allows solar wind energy to funnel directly into polar regions of the upper atmosphere, heating it and driving atmospheric escape. Each mechanism operates slowly on a human timescale. Each operates catastrophically on a geological one. Mars carries the evidence of what this process produces over billions of years. The Mars Global Surveyor spacecraft, which entered Martian orbit in September 1997 and spent years mapping the planet's surface and measuring its magnetic environment, returned data that settled a question planetary scientists had debated for decades. The measurements came from the spacecraft's magnetometer, and what they revealed was a Mars that no longer possessed a global magnetic field, only localized regions of strongly magnetized ancient crust, concentrated primarily in the southern highlands, their orientations varying from region to region in a pattern consistent with a field that had been active during the crust's formation and had then ceased. These crustal remnants are effectively a fossil field, the imprint of a dynamo that ran for perhaps the first 500 million years of Mars's history and then stopped, leaving only this static record in the oldest rocks. Janet Luhman at the University of California, Berkeley, spent much of her career modeling the interaction between the solar wind and planetary atmospheres, with particular attention to Mars and Venus. Her work helped establish the quantitative framework for understanding atmospheric loss rates at planets without global magnetic protection, the specific channels through which the solar wind removes atmospheric material, the dependence of those rates on solar activity, and the cumulative loss over geological time that results. The picture that emerged from her modeling and from subsequent spacecraft measurements was of a Mars that had been losing atmosphere continuously since its dynamo shut down, at rates that varied with the Sun's activity cycle, but never dropped to zero. The MAVEN mission, Mars Atmosphere and Volatile Evolution, was designed to measure those rates directly. Launched in November 2013 and managed by Bruce Yakosky at the University of Colorado, MAVEN spent years in a highly elliptical orbit that took it through the upper Martian atmosphere on each pass, directly sampling the ions escaping into space. The measurements it returned were specific. Mars loses approximately 100 grams of atmosphere per second to solar wind stripping under current conditions. The Sun is now a middle-aged, relatively stable star. When Mars was young, the Sun was more active, its solar wind more intense, its ultraviolet output higher, and the loss rates were almost certainly far greater. Jakosky and his team used MAVEN's data alongside solar evolution models to estimate the total atmospheric loss over Mars's history, and the numbers pointed toward a planet that had once possessed an atmosphere dense enough to support liquid water on its surface and had been slowly emptied over 4 billion years of unprotected exposure. The mechanism has a specific geometry that is worth understanding. Around Earth, the magnetic field creates a magnetosphere, a region of space dominated by Earth's field rather than the solar winds. The magnetosphere has a bow shock, where the solar wind is slowed and deflected, a magnetosheath, where deflected solar wind plasma flows around the obstacle, and a magnetopause, the boundary between the solar wind's domain and Earth's. Charged particles that penetrate this system, primarily through the polar cusps where field lines funnel toward the surface, produce the aurora, the visible signal of the interaction between the solar wind and the field that contains it. The aurora is, among other things, evidence that the system is working. The charged particles that would otherwise enter the atmosphere are being captured and channeled, their energy dissipated as light rather than as atmospheric heating and escape. Mars has no equivalent structure. The solar wind reaches the Martian upper atmosphere directly, with only a weak-induced magnetosphere, a structure created by the interaction of the solar wind with the ionosphere itself, offering some partial deflection, but nothing comparable to the protection a global field provides. The difference in outcome, measured in atmospheric surface pressure, is a factor of roughly 160 compared to Earth. That factor is not entirely attributable to the magnetic field. Mars's smaller gravity and greater distance from the Sun also play roles, but the magnetic field's absence is the central variable. Venus, with a similarly weak intrinsic field, maintains a dense atmosphere through a combination of volcanic outgassing and its greater mass. But Venus's story involves other failure modes, to be considered shortly. Michael Faraday's work in the 1830s established the foundational principles of electromagnetic induction, the relationship between moving conductors and magnetic fields that underlies the physics of every planetary dynamo. Faraday had no interest in planetary science. He was working with coils of wire and iron cores on a laboratory bench in London, mapping the invisible geometry of forces he could demonstrate but not yet fully explain. The planetary application came more than a century later, when the mathematics of magnetohydrodynamics, the behavior of conducting fluids in magnetic fields, was developed to the point where a planetary interior could be modeled as a natural dynamo. Faraday's experimental demonstrations of electromagnetic induction are the distant conceptual ancestor of every magnetic field measurement that MEVN and Mars Global Surveyor returned. In the same way that a long chain of physics connects a laboratory observation to a spacecraft measurement 150 million kilometers from Earth. What the data from Mars Global Surveyor and MEVN have established, taken together, is a precise account of a planetary death mechanism. Mars's interior cooled faster than Earth's. It is a smaller planet, and smaller planets lose their internal heat more rapidly. As the core cooled and the convection that drove the dynamo weakened, the global magnetic field decayed. The timeline appears to place this decay somewhere around 4 billion years ago, during a period when the sun was still young and active and the solar wind was at its most erosive. Without the field, the atmosphere that Mars had accumulated during its first half-billion years, denser, warmer, capable of supporting liquid water, began to be stripped away. The stripping was not instantaneous. It was a process that unfolded over hundreds of millions of years, the atmospheric pressure declining gradually, the temperature dropping as the greenhouse effect weakened, the liquid water retreating first to the poles, then underground, then disappearing from the surface entirely. The loss of the magnetic field did not kill Mars directly. It removed the protection that would have allowed Mars to retain the atmosphere that moderated its climate. What followed from that removal, the thinning of the air, the collapse of the greenhouse effect, the freezing and escape of the water, is the story that the surface of Mars now tells. In its valley networks and its ancient lakebeds and its chemical record of water that no longer flows. Reading that record required sending spacecraft, developing instruments sensitive enough to measure the faint signal of atmospheric ions escaping into space, and building physical models capable of running planetary history backward from the present ruins to the conditions that produced them. That reading, the reconstruction of a planetary death from its aftermath, is what modern Mars science has spent 50 years learning to do. The surface itself holds the archive of what was lost, and it is an archive more detailed and more legible than anything that could have been anticipated when the first spacecraft reached Mars in the 1960s. What Mariner 9 found when its cameras finally cleared the dust, and what Michael Carr's team spent years mapping from those images, is a record written in topography and chemistry, a record of water that moved, collected, carved, and then vanished over timescales that bracket the entire history of life on Earth. Chapter 3: The Atmosphere Mars Lost. On November 13, 1971, the Mariner 9 spacecraft became the first human-made object to achieve orbit around another planet. The achievement was immediately complicated. Mars was in the middle of a global dust storm, one of the largest ever recorded, a planet-wide suspension of fine particulate material that had been building since late September and had, by the time Mariner 9 arrived, completely obscured the surface. The cameras worked. There was nothing to photograph. Mission scientists at the Jet Propulsion Laboratory settled in to wait, monitoring the storm's slow dissipation from a distance of several 100 million kilometers, watching the atmospheric opacity measurements decline week by week until, in early January 1972, the surface began to emerge. What appeared first, through the clearing haze, were 4 dark spots arranged in a rough line, the summits of the Tharsis volcanoes, tall enough to protrude above the storm. Then the rest of the surface came through, and the geologist Michael Carr, working with the USGS Astrogeology Science Center, began mapping what the cameras showed. What Carr's team mapped over the following months was not the dead, crater-saturated surface that earlier Mariner flybys had suggested. The earlier missions had photographed portions of the ancient southern highlands, the most heavily cratered terrain on Mars, and the scientific community had largely concluded that Mars was a geologically inert world with no history more interesting than the one the Moon displayed. Mariner 9's global coverage showed something different. There were canyons wider and deeper than anything on Earth. There were volcanoes taller than any mountain in the solar system. And there were channels, branching, sinuous, valley networks covering millions of square kilometers of the ancient terrain, whose morphology was consistent with only one explanation. Liquid water had moved across the surface of Mars, not recently, not briefly, but in sufficient volume and over sufficient time to carve networks of valleys that, on Earth, would be recognized without hesitation as river drainage systems. The valley networks cover approximately 4.5 million square kilometers of Martian terrain, concentrated primarily in the ancient southern highlands, where the surface dates to the Noaean period, Mars's earliest geological epoch, spanning roughly 4.1 to 3.7 billion years ago. Their existence raised an immediate question. Mars today is far too cold and its atmosphere far too thin for liquid water to be stable on the surface. The current average surface temperature is around -60 degrees Celsius, and the atmospheric pressure of 0.636 kilopascals places Mars well below the triple point of water, the pressure below which liquid water cannot exist at any temperature, subliming directly from ice to vapor without passing through a liquid phase. Whatever conditions allowed those valleys to form no longer exist. Something changed, and the change was total. The chemical record of that change is preserved in the water vapor that Mars still holds in its thin atmosphere. Water molecules contain hydrogen, and hydrogen comes in two stable forms. Ordinary hydrogen, with a single proton in its nucleus, and deuterium, with a proton and a neutron. The two forms are chemically identical, but differ slightly in mass, and that mass difference matters for atmospheric escape. Lighter ordinary hydrogen escapes more easily than heavier deuterium when the solar wind and thermal processes drive atmospheric loss. Over time, as a planet loses water to space, the remaining water becomes progressively enriched in deuterium relative to ordinary hydrogen. The ratio of deuterium to ordinary hydrogen in Mars's current atmospheric water vapor is approximately 5 times the ratio found in Earth's oceans. That enrichment is a direct measurement of loss, a chemical record of ancient water that escaped, leaving its heavier isotope behind in steadily increasing concentration over billions of years. Tobias Owen at the University of Hawaii, working with spectroscopic data from Earth-based telescopes and later from spacecraft, was among the first to use the deuterium to hydrogen ratio as a tool for reconstructing Mars's water history. The logic is straightforward even if the measurement is technically demanding. The higher the DH ratio relative to Earth's, the more water has been lost. Owen and his colleagues' work helped establish that the water loss was ancient and enormous, not a recent event, but a process spanning most of Mars's geological history. Subsequent measurements from the CRISM instrument on the Mars Reconnaissance Orbiter and from the Curiosity rover's onboard mass spectrometer have refined the picture, confirming the enrichment and extending the analysis to ancient hydrated minerals whose DH ratios record the composition of water present at the time they formed, billions of years earlier. Mars's axial tilt introduces a further complication that Earth does not share in the same degree. Earth's axial tilt, currently 23.5 degrees, varies only slightly over long timescales, constrained by the gravitational influence of the Moon. Mars has no comparable stabilizing satellite. Its axial tilt varies between approximately 15 and 35 degrees over cycles of roughly 100,000 years, and over longer timescales the variation may be far more extreme. Some models suggest Mars's tilt has ranged from near zero to more than 60 degrees over its history. These variations drive dramatic swings in the distribution of solar energy across the planet's surface, periodically moving ice deposits between the poles and lower latitudes, altering the pressure and composition of the atmosphere as volatile materials cycle between surface reservoirs and the air above them. A Mars with a tilt near 45 degrees receives enough solar energy at its poles to sublimate significant quantities of the polar ice caps, temporarily thickening the atmosphere. A Mars with a tilt near zero concentrates ice at the poles, thinning the atmosphere further. The climate is not stable between glacial and interglacial states, as Earth's has been in a broad sense. It oscillates through a much wider range, driven by orbital dynamics that no moon is present to dampen. Bruce Jakosky and his MEVEN team have used measurements of the current atmospheric escape rate to work backward through this history. The approach requires modeling the Sun's past activity. It was significantly more active in its youth, producing a stronger solar wind and more intense ultraviolet radiation, and combining those estimates with Mars's current loss rates to reconstruct the cumulative loss over time. The results suggest that Mars lost the equivalent of a global ocean between 10 and 20 meters deep to space since the loss of its magnetic field, with additional water likely sequestered in the subsurface as permafrost and hydrated minerals. The atmosphere that Mars possessed during the Noachian period, dense enough to keep water liquid, warm enough through greenhouse effect to prevent its freezing, was gradually removed through the combined action of solar wind stripping, photochemical escape, and the slow decline of volcanic outgassing that had replenished it. The work of Horton Newsom and others examining the mineralogical record from Mars orbiters has added texture to this picture through the distribution of water-altered minerals across the Martian surface. Phyllosilicates, clay minerals that form through the prolonged interaction of rock with liquid water, are concentrated in the ancient Noachian terrain. Sulfates, which form in more acidic and episodic water conditions, are more common in younger Hesperian-era deposits. Anhydrous minerals, indicating little or no liquid-water interaction, dominate the youngest surfaces. The mineralogical sequence is a stratigraphic record of a planet drying out, each layer of rock recording the conditions of a progressively more desiccated world, the chemistry shifting from the signatures of abundant liquid water to the signatures of occasional liquid water to the signatures of almost none. Curiosity's traverse across Gale Crater, which was selected as a landing site precisely because it preserves a layered sedimentary record of ancient Mars, has provided the most detailed ground-level reading of this archive. The crater's central mound, Mount Sharp, consists of sedimentary layers deposited over hundreds of millions of years, and Curiosity has drilled into these layers systematically, extracting chemical and mineralogical data from rocks that formed during Mars's wetter periods. The lower layers contain minerals that require neutral pH liquid water to form, the kind of water that would not be immediately hostile to microbial life as we understand it. Higher layers record the transition to more acidic and oxidizing conditions. The sequence tells the story of a habitable environment becoming progressively less so, not through a single catastrophe, but through a long, slow, chemically recorded deterioration. The carbon dioxide that constituted the bulk of Mars's ancient atmosphere did not simply escape to space. Much of it was sequestered into carbonate minerals through reaction with liquid water and surface rock, a process that on Earth is part of the long-term carbon cycle that helps regulate global temperature. On Mars, the absence of active plate tectonics meant that these carbonates, once formed, were not subducted and recycled back into the atmosphere through volcanism the way they are on Earth. The carbon was locked away. As the atmosphere thinned, the greenhouse effect that had kept the surface warm enough for liquid water weakened, temperatures fell, The remaining liquid water froze, and the conditions that had allowed carbonate formation in the first place disappeared. The process was self-reinforcing, a feedback loop running in the direction of cold and thin and dry, with no mechanism to reverse it once it had progressed past a certain threshold. The dust storm that greeted Mariner 9 on arrival was, in its way, a demonstration of the end state of this process. Martian dust storms are possible precisely because the atmosphere, thin as it is, can still move fast enough to lift fine particles from the surface and keep them suspended. The low gravity and the low pressure together create conditions in which dust, once airborne, stays airborne for weeks. The particles themselves are the ground-up product of a surface that has been chemically weathering for billions of years without water to wash the products away, without rivers to carry sediment to oceans, without the biological and hydrological cycling that constantly reworks Earth's surface material. The dust is, in a sense, the residue of Mars's geological history, all the chemistry that happened when water was present, dried out, oxidized, and ground fine by billions of years of thermal cycling and wind. What Carr and his team mapped from Mariner 9's images, and what decades of subsequent missions have refined, is not simply the history of Mars. It is a detailed record of what happens to a world when the conditions for habitability are present briefly and then removed, when the magnetic field fails, the atmosphere thins, the water escapes, and the surface is left in the state that Mars now occupies: cold, dry, thin-aired, and chemically oxidized to a depth of several meters by the ultraviolet radiation that an intact atmosphere would have absorbed. Mars is not an alien place, it is a legible one. The record it preserves of a warmer, wetter past is the record of a set of conditions that Earth still maintains, and that Venus, by a different path and for different reasons, lost even more completely. Chapter 4: How Venus Became Uninhabitable. The surface of Venus sits under 92 atmospheres of pressure, the equivalent of being nearly a kilometer beneath Earth's ocean surface, and maintains an average temperature of approximately 465 degrees Celsius, day and night, pole to equator, with almost no variation. The temperature does not drop significantly on the night side because the atmosphere is so dense and so thoroughly mixed that it retains heat with an efficiency no other planetary atmosphere in the solar system approaches. Lead melts on the Venusian surface. The few Soviet Venera landers that survived long enough to transmit data from the surface lasted between 23 minutes and just over 2 hours before their electronics failed. The pressure and heat together make Venus the most hostile surface environment among the terrestrial planets, more hostile than Mercury, which, at least, has a cold night side. What makes Venus genuinely unsettling, in a way that Mars is not, is that this is almost certainly not how Venus began. On June 6, 1761, the planet Venus passed across the face of the Sun as seen from Earth, a transit, one of the rarest predictable astronomical events, occurring in pairs separated by 8 years and then not again for over a century. Observing teams had been dispatched to locations around the globe to time the transit from different positions, the data to be combined to calculate the distance from the Earth to the Sun through parallax. Mikhail Lomonosov, the Russian polymath who had already made foundational contributions to chemistry, physics, and literature, observed the transit from the St. Petersburg Academy of Sciences. He was watching for the precise moment Venus's disk made contact with the Sun's edge, the geometric measurement the parallax calculation required, and he noticed something the geometry alone did not predict. As Venus began to move off the solar disk at egress, A thin arc of light appeared around the portion of the planet's limb that had already cleared the Sun. The arc persisted briefly and then vanished as Venus moved further away. Lomonosov recognized what he was seeing: sunlight refracting through an atmosphere. Venus, he concluded, possessed an atmosphere comparable in density to Earth's. He was right, though neither he nor anyone else in 1761 had any means of knowing what that atmosphere contained or what it was doing to the surface beneath it. The contents of Venus's atmosphere remained largely unknown until the middle of the 20th century, when infrared spectroscopy developed to the point where ground-based telescopes could detect the signatures of specific molecules in planetary atmospheres from Earth. Carbon dioxide was identified as the dominant constituent of Venus's atmosphere in the late 1950s. What this meant for the surface temperature was not immediately obvious to everyone, but it was obvious to a young graduate student at the University of Chicago named Carl Sagan, who in 1960 began working through the implications in a paper that would be published in the Astrophysical Journal in 1961. Sagan's calculation was straightforward in principle. Carbon dioxide is a greenhouse gas. Venus has an enormous quantity of it, and the greenhouse effect would therefore drive the surface temperature far above what simple distance from the Sun would produce. He estimated surface temperatures in the range of 300 to 400 degrees Celsius, an underestimate, as it turned out, but a prediction that the subsequent Venera landers would confirm in kind, if not precisely in magnitude. The paper was Sagan's first significant scientific publication, and it demonstrated that Venus's extreme conditions were not mysterious, but were the quantitatively predictable consequence of its atmospheric composition. What Sagan's paper did not address, because the data did not yet exist to address it, was how Venus had arrived at that atmospheric composition. The question of Venus's history, and specifically whether it had ever been more like Earth, took decades longer to develop. The Magellan spacecraft, which mapped Venus's surface through its thick clouds using synthetic aperture radar between 1990 and 1994, returned images of a geologically young surface, one largely resurfaced by volcanic activity within the last 300 to 600 million years, with relatively few impact craters compared to what would be expected if the surface were ancient and unmodified. The volcanic resurfacing had effectively erased the geological record of Venus's early history. Whatever had happened in Venus's first 2 or 3 billion years, whether it had possessed oceans, whether liquid water had flowed, whether the surface had been more temperate, the evidence was buried under billions of years of subsequent volcanic activity. James Casting at Penn State University, whose work on planetary habitability will appear more fully in the next chapter, was among the researchers who turned to climate modeling to ask the question the geological record could not answer directly. Could Venus have been habitable in its past? The modeling approach requires specifying the Sun's luminosity at different points in the past. The Sun has been gradually brightening over its main sequence lifetime, and 4 billion years ago it was approximately 70% as luminous as it is today, and then calculating whether a Venus-like planet at Venus's orbital distance could have maintained surface liquid water under those conditions. Several studies published in the 2000s and 2010s, including work by Michael Way at the NASA Goddard Institute for Space Studies, suggested that the answer might be yes. A slowly rotating Venus. Its current rotation period is 243 Earth days, longer than its orbital period of 225 days, meaning Venus's day is longer than its year. Could, under certain conditions, have maintained thick cloud cover on its perpetual day side that reflected enough sunlight to keep surface temperatures moderate. If Venus formed with sufficient water and rotated slowly enough, the models suggested it might have remained habitable for as long as 2 to 3 billion years. The mechanism that ended this hypothetical habitability is less certain than the end state it produced. One candidate is simply the Sun's increasing luminosity over geological time. As the Sun brightened, the energy input to Venus's atmosphere increased until the rate of water evaporation exceeded the rate at which it could be returned through precipitation, triggering a runaway greenhouse effect. Water vapor itself is a potent greenhouse gas, and once sufficient water entered the atmosphere through evaporation, the warming it caused drove further evaporation, which drove further warming, in a feedback loop with no stabilizing mechanism to interrupt it. As the upper atmosphere warmed, water vapor reached altitudes where ultraviolet radiation could dissociate it into hydrogen and oxygen. The hydrogen, being light, escaped to space, and the oxygen either escaped or was absorbed into surface rock through oxidation. The oceans, if Venus had them, were gradually transferred to the atmosphere and then to space, leaving behind a dry surface and an atmosphere dominated by the carbon dioxide that volcanic outgassing had been contributing throughout Venus's history. Carbon that on Earth is cycled through the ocean and into carbonate rock, but on Venus, without liquid water to drive that cycling, accumulated in the atmosphere without limit. Giovanni Cassini, the Italian-French astronomer who spent decades at the Paris Observatory in the late 17th century and made foundational observations of Saturn, Jupiter, and Mars, observed Venus extensively and documented its phases and apparent size changes with the precision that characterized his work across planetary astronomy. Cassini had no way of knowing what Venus's surface conditions were, or that the brilliant white planet he observed through his telescopes was brilliant white because of its unbroken cloud cover of sulfuric acid droplets, clouds that reflect approximately 70% of incoming sunlight and make Venus the brightest object in the night sky after the moon, while simultaneously trapping the heat that reaches the surface. The clouds were understood to be clouds, in the sense of an opaque atmospheric layer, well before their composition was known. Their sulfuric acid content was determined in the early 1970s through infrared spectroscopy, a discovery that completed the picture of a surface environment that bore no resemblance to the speculative temperate Venus that some astronomers had imagined into the early space age. The Pioneer Venus mission, arriving in 1978, and the subsequent Magellan radar mapping added the detail that Venus's surface, while geologically young by planetary standards, shows evidence of extensive and possibly ongoing volcanic activity. The European Space Agency's Venus Express mission, which operated from 2006 to 2014, detected thermal anomalies in the southern hemisphere consistent with geologically recent or active lava flows. In 2020, a reanalysis of Magellan data by Laurent Montesi and colleagues identified what appeared to be a recently active volcanic vent, recent in geological terms meaning perhaps within the last few 100,000 years, which on planetary timescales is essentially contemporary. If Venus remains volcanically active, it is continuously outgassing carbon dioxide and sulfur dioxide into an atmosphere that has no mechanism to remove them. The process that made Venus what it is has not necessarily stopped. Venus rotates in the opposite direction to most planets in the solar system. If you could stand on its surface and see the sun through the clouds, it would rise in the west and set in the east. Moving slowly across a sky it takes 117 Earth days to cross. The retrograde rotation is almost certainly the result of a large impact or gravitational interaction early in Venus's history, and it may be relevant to the planet's current state in ways that are still being modeled. A faster rotating Venus with a different atmospheric circulation pattern might have developed a magnetic field. Its current slow rotation produces a core that may lack the convective vigor needed to sustain a dynamo. Without a magnetic field, Venus loses atmosphere to solar wind stripping, more slowly than Mars, because Venus's greater mass and denser atmosphere make the stripping less efficient, but continuously. Venus is losing its atmosphere by the same mechanism that stripped Mars, just at a slower rate and from a much larger reservoir. What Venus represents, in the context of this episode's inventory of failure, is the case of a world that may have had everything: mass, water, the right distance from its star, billions of years of potential habitability, and lost it through a combination of orbital dynamics, solar evolution, and the absence of the specific geological recycling mechanism that has kept Earth's carbon dioxide out of the atmosphere and in the rock. The difference between Venus and Earth in this reading is not primarily one of size or distance or composition, but of whether the carbon silicate cycle, the long-term geological thermostat that draws carbon dioxide out of the atmosphere through weathering, deposits it in ocean sediments, and returns it through volcanic outgassing, remained functional. On Earth, plate tectonics drives that cycle. On Venus, whatever equivalent process may have operated appears to have failed, or may never have operated the same way, and the result was an atmosphere that accumulated greenhouse gases without limit until the surface reached the state the Venera landers found. The carbon silicate cycle is not a given. It requires liquid water to drive weathering, an oceanic sink for carbon, and a mechanism, on Earth, subduction, to return the sequestered carbon to the mantle where it can be outgassed again. Remove any one of those components and the cycle stalls. On a world where the cycle stalls, carbon dioxide accumulates, temperatures rise, water escapes, and the cycle cannot restart because the liquid water it requires is gone. Venus shows us what that endpoint looks like, at planetary scale, over geological time. It is a world that passed through a threshold, perhaps gradually, perhaps over tens of millions of years, from which no natural recovery was possible. The threshold itself is the subject that James Casting spent much of his career trying to locate precisely, and locating it required building the concept of the habitable zone from something intuitive into something calculated. Chapter 5: The Narrow Window. Across the Milky Way, there are somewhere in the range of 100 billion stars. They vary enormously in mass, temperature, luminosity, and lifespan, from massive blue giants that burn through their fuel in a few million years and die in supernovae, to dim red dwarfs that will still be fusing hydrogen long after the sun has expanded into a red giant and consumed the inner planets. Around most of these stars, planets have formed. The Kepler mission established this with enough statistical weight to treat it as a settled question. Planets are not rare accompaniments to unusual stars, but the ordinary products of star formation, present around the majority of stellar systems in configurations that vary with the star's mass and the disk conditions at the time of formation. The question of which of those planets might support life is therefore not primarily a question about planetary frequency. Planets are common, but about the specific conditions a planet must maintain, and for how long, and how narrow the range of conditions that allows them to be maintained actually is. James Casting arrived at this problem from atmospheric chemistry. His doctoral work in the late 1970s and early 1980s focused on the evolution of Earth's early atmosphere, the chemical transformations that took a reducing, largely anoxic early atmosphere toward the oxygenated one that exists today, and the modeling tools he developed for that work were directly applicable to the question of what atmospheric conditions allow liquid water to persist on a planetary surface. By the late 1980s, Casting had turned his attention explicitly to the boundaries of habitability. At what distance from a given star does a planet become too hot for liquid water to remain liquid? And at what distance does it become too cold? The question sounds simple, but had not been answered with any quantitative rigor. Estimates existed, The concept of a stellar habitable zone had been discussed since the 1950s and 1960s, with early contributions from Harlow Shapley and later from Stephen Dole, but they were based on intuitive reasoning rather than atmospheric modeling, and they varied enough between authors to suggest that nobody had done the calculation carefully. Casting did the calculation carefully. Working with Daniel Whitmire and Ray Reynolds, he published a paper in Icarus in 1993 that became the foundational reference for the field of planetary habitability. The approach was to model a simplified but physically realistic planetary atmosphere, specifying the composition, the stellar flux, the atmospheric pressure, and the feedback mechanisms that regulate surface temperature, and then vary the planet's distance from its star until the model atmosphere either entered a runaway greenhouse state, with water vapor accumulating until the oceans evaporated, or a snowball state, with carbon dioxide condensing out of the atmosphere and the planet freezing entirely. The boundaries of the habitable zone were defined by these two failure modes: too close, and the planet becomes Venus; too far, and it becomes a frozen world from which there may be no recovery. Between them, liquid water could persist on the surface indefinitely. For a star like the Sun, Casting, Whitmire, and Reynolds found the habitable zone extended from approximately 0.95 astronomical units, just inside Earth's current orbit, to approximately 1.37 astronomical units, well beyond Mars's orbit at 1.52 AU. Mars, by this calculation, was outside the habitable zone not because of its distance, but because of its failure to maintain the atmospheric pressure and composition that would have kept it warm enough for liquid water. A distinction that matters because it separates the question of where a planet is from the question of what it can maintain. Earth, at 1.00 U, sits comfortably within the calculated zone, but the paper's most consequential finding was not the zone's outer or inner edge, but a subtler boundary hidden within it. The continuously habitable zone, the region within which a planet remains habitable not just at a single moment, but over the entire multi-billion-year lifespan of its star. The continuously habitable zone is narrower than the instantaneous habitable zone because stars evolve. The Sun has been brightening throughout its main sequence lifetime. It is approximately 30% more luminous now than it was 4.5 billion years ago when the solar system formed, and it will continue to brighten over the next several billion years. A planet that is comfortably within the habitable zone today may have been marginally outside the inner edge of the habitable zone, too close, in danger of a runaway greenhouse, when the star was younger and dimmer, or may be pushed outside the inner edge as the star continues to brighten. Conversely, a planet near the outer edge of the habitable zone today may have been too cold for liquid water early in the star's history. The continuously habitable zone, the range of orbital distances at which a planet remains habitable from the star's birth through the present, narrows, for a Sun-like star, to roughly 0.95 to 1.15 astronomical units. Earth sits within this narrower band. Mars does not. Venus does not. The band that contains Earth is approximately 30 million kilometers wide around a Sun-like star, wide in absolute terms, narrow as a fraction of the distances involved. Ravi Kopparapu at the NASA Goddard Space Flight Center revisited Casting's calculation in 2013 with updated spectroscopic data for water vapor and carbon dioxide absorption, the molecular parameters that determine how efficiently these gases trap heat, and found that the boundaries shifted somewhat. His revised habitable zone extended from approximately 0.99 to 1.70 astronomical units for a Sun-like star, with the inner edge moving slightly outward and the outer edge moving significantly outward compared to Casting's 1993 estimates. The revision mattered because it affected the classification of specific known exoplanets, Some that had been considered marginal cases moved clearly into the habitable zone, and some that had been considered outside moved in. Kopperapu's paper became the standard reference for exoplanet habitability assessments and has been downloaded and cited more than almost any other paper in its field. The felt quality of the habitable zone is not warmth. Exactly. It is the quality of water's state. Within the habitable zone, water exists in all three phases on a planetary surface: liquid in oceans and rivers, solid as ice at the poles and in mountains, vapor in the atmosphere. It is this cycling among states that drives the geological and chemical processes that regulate long-term climate. Rain weathers rock, releasing minerals that react with carbon dioxide, drawing it out of the atmosphere and into the ocean as dissolved bicarbonate. Ocean chemistry deposits that carbon as carbonate rock. Subduction carries the rock into the mantle. Volcanism returns the carbon dioxide to the atmosphere. The cycle operates on timescales of hundreds of thousands to millions of years and acts as a thermostat. When temperatures rise, weathering accelerates. More carbon dioxide is drawn down, and temperatures fall. When temperatures fall, weathering slows. Volcanic outgassing accumulates, and temperatures rise. This thermostat requires liquid water at the surface to function. Outside the habitable zone, where water is permanently ice or permanently vapor, the thermostat stalls, and temperature regulation through the carbon silicate cycle fails. The habitable zone is, in this deeper sense, the zone within which geology can regulate climate over geological time. Guillermo Gonzalez, then at Iowa State University, extended the concept in a different direction in the late 1990s and early 2000s, proposing that position within the galaxy, not just position around a star, constitutes an additional habitability filter. The galactic habitable zone, as Gonzalez defined it, occupies a band in the Milky Way's disk at intermediate distances from the galactic center, far enough from the center that the density of stars, supernovae, and gamma-ray bursts is not so high as to sterilize planetary surfaces through radiation, but close enough that the heavy elements necessary for rocky planet formation and biological chemistry are present in sufficient abundance. The galactic center is chemically rich but radiatively violent. The galactic outskirts are quiet but chemically poor, with too little iron, silicon, and carbon to build Earth-like planets in the first place. Earth's position in the Orion Arm, approximately 27,000 light-years from the galactic center, places it in a region Gonzalez argued was neither too rich nor too poor, neither too violent nor too quiet. A galactic habitable zone within which the conditions for planetary habitability are, on average, better than elsewhere in the disk. The galactic habitable zone concept was extended and placed on more quantitative footing by Charles Linweaver at the Australian National University, who in 2004 published an analysis estimating what fraction of stars in the Milky Way formed at the right time, in the right place, with the right chemical abundances to host potentially habitable planets. Lineweaver's estimate was that roughly 9% of the Milky Way's stars fell within the galactic habitable zone during the window of time when complex life could in principle have developed, a significant fraction of 100 billion stars, but a much smaller fraction than naive estimates of planetary frequency would suggest. The galactic habitable zone added another layer to the filter. Not every star in the habitable zone of its galaxy produces the right heavy element abundances, and not every planet in the habitable zone of its star has those elements distributed in the right proportions to build a geologically active, chemically complex world. Casting's 1993 paper had been built on data and modeling techniques that were the best available at the time, but acknowledged their own limitations. The atmospheric models were one-dimensional. They treated the planet as a uniform sphere with a single representative column of atmosphere, rather than modeling the three-dimensional circulation of a real atmosphere. The feedback mechanisms were simplified. The range of planetary compositions was limited to Earth-like values. In the 3 decades since the paper's publication, the models have become far more sophisticated, incorporating three-dimensional general circulation models, a wider range of atmospheric compositions, the effects of clouds, and the influence of planetary rotation rate on climate. The general structure of Casting's result has held. There is a habitable zone. Its boundaries are roughly where he placed them, and the continuously habitable zone within it is narrower. But the details have been revised, and the revisions have mostly moved the boundaries outward, suggesting that the zone is somewhat more generous than the 1993 paper found. The patience that Casting's work required was of a specific kind. It was the patience of defining the boundaries of a region before having the instruments to observe whether anything lived inside it. For most of the 2 decades between the 1993 paper and the Kepler mission's first results, the habitable zone was a theoretical construct applied to stars whose planets could not be detected. The zone was mapped. What it contained remained unknown. This is not an unusual situation in planetary science, where theory routinely runs ahead of observation, where the mathematics of what should exist is developed in detail long before spacecraft or telescopes can reach the places the mathematics describes. Casting was, in a sense, marking territory on a map that would only slowly fill in. As detection methods improved and the first catalogues of exoplanets began to grow from dozens to hundreds to thousands of confirmed worlds, what the Kepler mission eventually found when it surveyed those worlds, and what the statistical picture of planetary demographics revealed about the frequency of Earth-like planets in habitable zones, is a thread that will return in Chapter 9. The next chapter, though, turns from the question of where a planet must be to the question of what Earth itself has survived, the moments in its own history when the conditions that make it habitable nearly failed, and what the recovery from those near failures required. Chapter 6: Snowball Earth and the Knife Edge Recoveries. Roughly 2.4 billion years ago, Earth froze. Not partially, not a glaciation of the kind that periodically advances ice sheets from the poles toward the temperate latitudes, the kind that buried much of North America and Europe under kilometers of ice as recently as 20,000 years ago. This was something of a different order, a glaciation that reached the equator, covering the oceans with ice to depths of perhaps a kilometer in the high latitudes and hundreds of meters even at the tropics, leaving the planet's surface as reflective as a mirror and the chemistry of the atmosphere and ocean altered in ways that would take tens of millions of years to fully resolve. The evidence for it is preserved in ancient glacial deposits found on every continent, including rocks formed at tropical latitudes that carry the unmistakable signatures of glacial grinding and transport: striations, dropstones, tillites, alongside the chemical record of an ocean that had nearly stopped cycling. Earth did not merely cool. It entered a state from which, by some analyses of the relevant physics, it should not have been able to exit. The geological evidence for extreme Precambrian glaciations had been accumulating since the middle of the 20th century. W. Brian Harland at the University of Cambridge spent much of the 1960s documenting glacial deposits of Precambrian age in Svalbard and other high-latitude regions, and arguing that the glaciations they recorded were more extensive than anything in the subsequent geological record. Harland's evidence was taken seriously as a record of ancient cold, but was not initially interpreted as evidence of a global freeze. The possibility that ice had covered the entire planet, including the tropics, seemed physically implausible to most of his contemporaries. The difficulty was thermodynamic. A fully ice-covered Earth would reflect so much sunlight that, by standard climate models, The planet could never warm again. If Earth had once been completely frozen, what had thawed it? The answer came from geochemistry, and the person who assembled it most forcefully was Paul Hoffman at Harvard University. Hoffman had spent years doing fieldwork in the Namibian desert, mapping a sequence of ancient rocks, the Otavi Group, that recorded a glaciation ending approximately 635 million years ago. What interested Hoffman was not merely the glacial deposits themselves, but what lay immediately above them, a layer of carbonate rock, pale and fine-grained, draped conformably over the glacial surface like a blanket. These cap carbonates, as they are known, are found worldwide atop glacial deposits of the same age, and they are geochemically strange. Their carbon isotope ratios show enormous excursions, shifts of 5 to 10 parts per thousand in the ratio of carbon-13 to carbon-12, written in the shorthand notation as delta 13C values ranging from -5 to -10 per mil, that record a profound disruption of the global carbon cycle. Normal marine carbonates form in an ocean whose surface waters are in approximate chemical equilibrium with the atmosphere and with the biological productivity of the photic zone. The cap carbonates above snowball glaciations record an ocean that had been sealed beneath ice for millions of years, cut off from the atmosphere, its chemistry drifting far from equilibrium, and then exposed suddenly when the ice melted. Hoffman published his interpretation in Science in 1998 in a paper co-authored with Alan Kaufman, Galen Halvorsen, and Daniel Schrag. The paper argued that the Neoproterozoic glaciations, particularly the Sturtian glaciation ending around 700 million years ago and the Marinian ending approximately 635 million years ago, represented complete or near-complete glaciations of Earth's surface, and that the cap carbonates above them recorded the aftermath of deglaciation driven by the accumulation of volcanic carbon dioxide beneath the ice over millions of years. The argument was received with a mixture of serious engagement and vigorous skepticism. The physical implausibility of global deglaciation was acknowledged. Hoffman and Schrag's answer to it was that volcanic outgassing, which continued throughout the glaciation because it is driven by the internal heat of the planet rather than by surface conditions, would have slowly built up atmospheric carbon dioxide to concentrations perhaps 300 times higher than today. Enough, eventually, to overwhelm the reflectivity of the ice and drive temperatures above freezing, triggering a deglaciation that, once started, proceeded rapidly. The coinage of the term snowball Earth belongs to Joseph Kirschvink at the California Institute of Technology, who had proposed the concept of a fully frozen Earth in a brief and characteristically direct paper in 1992. Several years before Hoffman's more elaborated geological argument appeared, Kirschvink had arrived at the idea from paleomagnetic evidence, the orientations of magnetic minerals in ancient rocks, which record the latitude at which those rocks formed, and had recognized that glacial deposits formed at equatorial latitudes in the Neoproterozoic implied ice coverage extending well into the tropics. His 1992 paper named the concept, outlined the basic physical mechanism for both glaciation and deglaciation, and proposed that the geochemical aftermath of a snowball event would include precisely the kind of carbonate deposits that Hoffman would later analyze in such detail. The intellectual relationship between Kirschvink's concept and Hoffman's evidence was one of the more productive convergences in late 20th century earth science, a theoretical prediction and an empirical dataset finding each other across a 6-year gap. The Huronian glaciation, which predates the Neoproterozoic snowball events by nearly 2 billion years, is older, less well preserved, and in some respects more puzzling. It began approximately 2.4 billion years ago and persisted through what may have been multiple glacial interglacial cycles, until roughly 2.1 billion years ago, a span of perhaps 300 million years, making it the longest glaciation in Earth's record. The timing places it immediately after the Great Oxidation Event, the period roughly 2.4 to 2.0 billion years ago, when the concentration of free oxygen in Earth's atmosphere rose from trace levels to amounts detectable in the geological record. The connection between the two events is causal and well supported. The rise of cyanobacteria, photosynthetic bacteria that produce oxygen as a metabolic byproduct, flooded the atmosphere with a gas that reacted readily with the methane that had previously constituted a significant portion of Earth's greenhouse warming. As methane was oxidized to carbon dioxide and water, the greenhouse effect weakened, temperatures fell, and the climate entered a glaciation that may have been more severe than any that followed. The Huronian glaciation is, in this reading, a case in which life itself nearly killed the planet it inhabited. The cyanobacteria did not intend to alter the climate. They had no intentions, only metabolic processes, but the cumulative effect of their oxygen production on an atmosphere calibrated to a different chemical balance was a climate catastrophe that approached the snowball threshold. Whether it fully crossed that threshold, whether ice reached the equator during the Huronian, as it apparently did during the Neoproterozoic snowball events, remains uncertain, because the geological record from 2.4 billion years ago is fragmentary and incompletely preserved. What is clear is that Earth's climate was destabilized severely, that the destabilization lasted for an enormous span of time, and that the recovery required the same volcanic carbon dioxide accumulation mechanism that eventually deglaciated the Neoproterozoic snowball events. The felt quality of a fully glaciated Earth is not cold in any ordinary sense of the word. Cold implies a range, a departure from something warmer, a condition that might be reversed by proximity to a heat source. What the snowball represents is a different kind of condition, a stability achieved through a different configuration of the planet's energy budget, in which the ordinary mechanisms of climate regulation have ceased to function and a new equilibrium has established itself. The ice reflects sunlight back to space with an efficiency that overwhelms the greenhouse warming from the carbon dioxide and methane remaining in the atmosphere. The ocean beneath the ice continues to circulate slowly, driven by geothermal heat from below, but its connection to the atmosphere is severed. The carbon cycle, which on an ice-free Earth moves carbon continuously through the atmosphere, ocean, and rock on timescales of thousands to millions of years, has slowed to a fraction of its normal pace. The planet is still, in the geological sense, not dead, but held in a configuration that resists change until enough volcanic carbon dioxide has accumulated to force a transition. The deglaciation, when it came, was rapid. The same reflectivity that made the snowball stable worked in reverse once temperatures rose above the melting point. Melting ice exposed darker ocean and rock, which absorbed more sunlight, which melted more ice, in a feedback loop that ran in the warming direction as forcefully as it had previously run in the cooling direction. The transition from fully glaciated to largely ice-free may have taken only a few thousand years, geologically instantaneous, though still far beyond any human frame of reference. The cap carbonates that blanket the glacial deposits worldwide were laid down during this transition and its immediate aftermath, as the carbon dioxide-rich atmosphere reacted with the newly exposed ocean surface in a burst of carbonate precipitation that, in Namibia and in equivalent sequences on other continents, produced layers of calcium carbonate deposited in perhaps 10,000 years, a rate of carbonate accumulation far exceeding anything that occurs under normal ocean chemistry. What followed the Marinian deglaciation, approximately 635 million years ago, is among the most consequential sequences in Earth's biological history. The Ediacaran period, which began at the end of the Meridian glaciation, records the first unambiguous evidence of complex multicellular organisms in the fossil record. Soft-bodied creatures of uncertain affinity, preserved in fine-grained sediments in Namibia, Newfoundland, and the Ediacaran Hills of Australia, that represent the earliest known experiments in multicellular body plans. The connection between the end of the snowball glaciations and the emergence of complex multicellular life is a subject of active research and genuine uncertainty. Whether the glaciations drove the evolution of complexity by fragmenting populations and imposing selective pressures, or whether the geochemical changes that followed deglaciation made complex life possible by altering ocean chemistry, or whether the timing is partly coincidental, remains unresolved. What is clear is that complex life did not appear before the snowball events and did appear after them, and that whatever the causal relationship, the glaciations occupy a position in Earth's biological history at which something fundamental changed. Peter Ward at the University of Washington, whose work on mass extinctions and the conditions for complex life spans several decades and several books, has framed the snowball events as part of a broader pattern in which Earth's habitability has been precarious rather than guaranteed. A planet that has passed through multiple near catastrophes and recovered each time through specific, non-obvious geochemical feedbacks. Ward's framing resists the comfortable narrative in which Earth's long history of life demonstrates that habitability is robust and self-sustaining. The snowball events suggest instead that habitability is a condition that must be actively maintained by the planet's own geochemical systems, and that there have been moments, some of them lasting hundreds of millions of years, when those systems nearly failed to maintain it. The recovery from each snowball event required that certain conditions continue to hold during the glaciation itself. Volcanic outgassing had to persist. If the internal heat driving volcanism had diminished below a certain threshold during a snowball, carbon dioxide accumulation might have stalled before reaching the concentration needed for deglaciation. Hydrothermal vents on the ocean floor continued to release heat and chemical energy into the water beneath the ice, maintaining the chemical disequilibrium that allowed microbial life to persist through the glaciation in these deep water refugia. Had those vents been absent, or had the ocean frozen solid rather than retaining liquid water beneath the ice, the biological record might have been reset entirely. The survival of life through the snowball events depended on the particular geometry of Earth's interior heat budget, on the depth of the oceans, and on the specific chemical properties of water that allow it to remain liquid at the base of an ice column even when the surface is frozen. The same mechanisms that nearly killed the planet also, in ending, may have set the conditions for the biological complexity that followed. Whether that connection is causal or contingent, the snowball events stand as the clearest demonstration in Earth's own geological record that habitability is not a permanent state but a balance maintained by interlocking systems, each of which, failing, can drag the others toward a new and less hospitable equilibrium. Understanding how those systems operate on Earth and how they have failed on Mars and Venus required the development of an entirely new kind of science, one that did not exist as a coherent field until the middle of the 20th century, and that was built, piece by piece, by a set of scientists who had to invent their tools before they could use them. Chapter 7. The Scientists Who Learned to Read Dead Planets. Gerard Kuiper was born in the Netherlands in 1905 and trained as an astronomer at Leiden University under Einar Hertzsprung, one of the architects of the classification system that still organizes stellar astrophysics. He emigrated to the United States in 1933 and spent the following decades doing something that most of his contemporaries considered a secondary pursuit: studying the planets. In the mid-20th century, planetary science did not yet exist as a coherent discipline. The planets were astronomical objects, observed from Earth through telescopes, and the tools available for studying them were limited to what could be measured in the light they reflected or emitted. There were no spacecraft. There were no in situ measurements. There was no way to land an instrument on another world or send a camera into orbit around one. What there was, for Kuiper and the handful of researchers who shared his interest, was spectroscopy, the decomposition of light into its component wavelengths, each wavelength carrying the signature of specific molecules in the atmosphere through which the light had passed. In 1944, Cooper turned his spectrograph toward Mars and identified an absorption feature in the reflected light that matched the signature of carbon dioxide. The detection was not the first claim of atmospheric features on Mars. Water vapor had been tentatively identified decades earlier, but it was among the most technically rigorous, and it established carbon dioxide as a confirmed constituent of the Martian atmosphere at a time when the atmosphere's composition was still largely unknown. 2 years later, Kuiper identified carbon dioxide in the atmosphere of Venus as well, a detection that would later become foundational to Sagan's greenhouse calculations. Cooper went on to detect methane and ammonia in the outer planets' atmospheres, to discover Miranda and Nereid as moons of Uranus and Neptune respectively, and to propose the existence of a belt of icy bodies beyond Neptune's orbit, a population now confirmed and bearing his name. But his planetary atmosphere work from the 1940s is the thread that connects most directly to the science of habitability, because it established that other worlds had chemically distinct atmospheres whose compositions could be read from Earth, and that reading them carefully would tell you something important about conditions at the surface. Carl Sagan arrived at planetary science from a different direction, through biology and the question of life's origins. His doctoral thesis at the University of Chicago, completed in 1960, addressed the physical conditions on the early Earth and their implications for the origin of life, a subject that required him to think carefully about atmospheric chemistry, surface temperature, and the energy sources available to drive prebiotic reactions. From there, the step toward planetary atmospheres was natural. Sagan's 1961 Venus greenhouse paper has already appeared in this chronicle, but the full scope of his early career in planetary science extends considerably beyond that single publication. Through the 1960s, he worked on the atmospheric composition of Jupiter, on the nature of Mars's surface color changes, on the possibility of life in the Jovian atmosphere, and on what the seasonal variations observed on Mars might indicate about the planet's surface chemistry. He collaborated extensively with Tobias Owen, a spectroscopist at Stony Brook University who had particular expertise in the atmospheres of the outer planets and who brought a rigorous observational discipline to work that Sagan often approached from a more theoretical direction. Owen's contributions to planetary atmosphere science across a career spanning 4 decades included spectroscopic identifications of atmospheric constituents on Titan, Pluto, and the outer planet moons, as well as work on the nitrogen-dominated atmospheres of Titan and Earth that helped clarify the conditions under which nitrogen accumulates as a dominant atmospheric component rather than being locked in mineral compounds or biological reservoirs. His collaboration with Sagan on the Voyager mission's scientific objectives, both served on the scientific teams for Voyager 1 and 2, placed them in the unusual position of helping define the questions that humanity's first detailed survey of the outer solar system would attempt to answer. The Voyager spacecraft, launched in 1977 and conducting their grand tour of the outer planets between 1979 and 1989, returned data from Jupiter, Saturn, Uranus, and Neptune, along with close observations of dozens of their moons, that transformed the outer solar system from a set of telescopic abstractions into a collection of specific, varied, chemically and geologically complex worlds. What Voyager showed, among much else, was that the solar system's moons were not geologically dead objects, but active ones. That Io was volcanically erupting in real time. That Europa showed surface features consistent with a liquid layer beneath its ice. That Titan had a thick nitrogen atmosphere with complex organic chemistry occurring in its upper layers. That Triton had geysers erupting from its nitrogen ice surface. The diversity of worlds the Voyager data revealed was not what had been expected, and it had an immediate effect on how planetary scientists thought about habitability. It expanded the range of environments where interesting chemistry and potentially biology might operate. From the narrow category of Earth-like rocky planets in habitable zones to a much broader set of environments defined by the presence of liquid, chemical energy sources, and the molecular building blocks of biological chemistry. Nathalie Cabrol grew up in France and came to planetary science through geology and the question of water on Mars, eventually joining the NASA Ames Research Center and the SETI Institute. Her specific contribution to the science of habitability involved not telescopes or spacecraft, but boots on the ground, or more precisely, waders in extremely cold, extremely high-altitude lake water. Cabrol identified the high-altitude crater lakes of the Atacama Desert in the Andes of northern Chile and southern Bolivia as the closest terrestrial analogues to the environments that may have existed on Mars during its Noachian period. Environments characterized by intense ultraviolet radiation, low atmospheric pressure, high salinity, extreme temperature fluctuation between day and night, and chemical conditions that would be considered hostile by the standards of most terrestrial ecosystems. Her fieldwork at Licancaba volcano's summit crater lake, at an altitude of 5,916 meters, the highest lake in the world, involved measuring the UV radiation reaching the water surface, sampling the microbial communities that survived in it, and comparing the lake's chemistry and biology to what Mars's ancient lake environments might have resembled. The UV measurements at Licancaba were striking in their own right. At that altitude, with a thinner column of atmosphere above the surface and the high-altitude Atacama air containing less ozone than lower elevation sites, the ultraviolet radiation intensity at the lake surface was approximately 50% higher than at sea level under equivalent solar conditions. The microbial communities in the lake had developed biochemical adaptations to survive that radiation: pigmentation, DNA repair mechanisms, protective compounds. But they were at the edge of what microbial life can tolerate. Cabrol's work used these communities as a calibration point. If life could persist at the UV intensities measured at Licancaba, what did that imply about the survivability of surface life on early Mars, where the atmosphere was thinner and the magnetic field weaker? The answer, her data suggested, was that even during Mars's wetter period, surface life would have faced UV challenges severe enough to drive it toward the subsurface or into sheltered niches, behind rocks, beneath thin layers of ice, in sediment rather than open water. The Atacama fieldwork did not resolve the question of life on Mars, but it gave the question a quantitative edge it had previously lacked. The development of planetary science as a coherent discipline required more than individual researchers working in isolation on specific questions. It required institutions, funding structures, spacecraft programs, and the organizational infrastructure to coordinate the work of thousands of scientists across decades. The founding of NASA in 1958 and the subsequent development of planetary exploration as a government-funded scientific program created the conditions in which planetary science could mature from an observational astronomy sideline into a field with its own spacecraft, its own instruments, its own training pipelines, and its own theoretical frameworks. The Mariner, Pioneer, Viking, Voyager, and Magellan missions were not simply spacecraft programs. They were, collectively, the construction of a new way of knowing, in which the planets moved from being points of light in a telescope to being places with surfaces, atmospheres, geologies, and histories that could be mapped and measured. Viking, in particular, stands as a turning point in the human relationship to the question of life on other worlds. The two Viking landers arrived on Mars in the summer of 1976, each carrying a suite of biology experiments designed by a team led in significant part by Gilbert Levin, designed to detect the metabolic signatures of microbial life in the Martian soil. One of the experiments, the labeled release experiment, which added a nutrient solution to a soil sample and measured whether carbon dioxide was produced through metabolic activity, returned a positive result. The soil consumed the nutrients and produced gas, which is what a sample containing living microbes would do. The result was immediately controversial. The gas production was energetic at first and then stopped, which was inconsistent with a biological interpretation. Living organisms should continue metabolizing as long as nutrients are available. The prevailing interpretation, developed in the years following the mission, was that the result reflected the chemical reactivity of Martian soil, which contains perchlorate compounds and other strong oxidants capable of producing the observed gas production through purely chemical reactions. Most planetary scientists accept the non-biological interpretation. Levin maintained for the rest of his life that the result was ambiguous and that biology had not been ruled out. The Viking biology experiments remain the only direct test of Martian soil for biological activity ever conducted, and their results remain the most discussed and contested data in the history of astrobiology. The transition from reading planets through Earth-based telescopes to reading them through orbiting spacecraft and surface landers compressed an enormous amount of scientific progress into a relatively short time. Between Kuiper's carbon dioxide detection in 1944 and the Mariner 9 global mapping in 1972, roughly 28 years elapsed, a span in which Mars went from a poorly characterized telescopic object to a world with a mapped surface, a measured atmosphere, and a documented record of ancient water. Between the Mariner 9 maps and the MIVEN atmospheric escape measurements, another 40 years elapsed, during which the question shifted from whether Mars had once been wetter to precisely how much water it had lost, through which mechanisms, and over what timescale. The science deepened, the questions narrowed, the answers became more specific. What Kuiper could only infer from the presence of carbon dioxide in a reflected spectrum, MAVEN measured directly in escaping ions above the Martian exosphere. The scientists who built this progression were not, for the most part, working on a single coherent program with a defined endpoint. They were working on the questions that their particular instruments and methods allowed them to approach, and the cumulative structure of what they found emerged from the accumulation of individual results rather than from a central plan. Sagan and Owen arguing over what Voyager should look for. Cabral carrying sampling equipment up a volcano at 5,000 meters to measure UV in a lake nobody had studied carefully. Joukowsky spending years getting MAVEN funded, built, and launched, and then spending more years processing the data it returned. The picture of dead and dying worlds that this episode has been assembling did not exist as a picture until enough individual pieces had been collected and placed in relation to each other. Each piece required someone patient enough to go and get it. That patience, the willingness to work on questions whose answers arrive slowly, in increments, across careers and generations, is the characteristic disposition of the scientists who built planetary science. It is also, as it happens, the disposition required to look at the outer solar system's moons and recognize that the question of habitability did not end at the inner edge of the frost line but extended outward, into the cold, to places where the warmth that mattered came not from sunlight but from the grinding of rock against rock in the interior of a moon held in gravitational tension by a giant planet. Chapter 8: Europa, Enceladus, and the Underground Possibility. Europa is slightly smaller than Earth's moon, orbits Jupiter at a distance of roughly 671,000 kilometers, and receives so little sunlight at that distance that its surface temperature averages around -160 degrees Celsius. By every criterion that defined planetary habitability through most of the 20th century, proximity to a star, surface temperature, atmospheric pressure, the possibility of liquid water at the surface, Europa is not a candidate. Its surface is ice. Its sky, such as it is, contains almost no atmosphere. The sunlight reaching it is about 25 times weaker than what reaches Earth. Nothing about its exterior, examined in isolation, suggests that it belongs in a conversation about living worlds. The Galileo spacecraft, which entered Jupiter orbit in December 1995 and spent the following 8 years making repeated flybys of the Galilean moons, did not confirm that Europa was habitable. What it confirmed was that the criteria needed to be reconsidered. The evidence accumulated over Galileo's mission through several independent lines. The surface of Europa, imaged in detail for the first time, showed a pattern of linear features, ridges, bands, and fractures that resembled, in their geometry, the surface of sea ice on Earth that had been broken, shifted, and refrozen. The features implied that the ice had moved and that something beneath it was capable of causing that movement. Either a liquid layer, whose tidal deformation of the ice shell above it could produce the observed fracture patterns, or a warm, ductile ice layer close enough to melting that it deformed under stress rather than fracturing cleanly. The magnetic field measurements, made during each flyby by Galileo's magnetometer, provided a more definitive answer. Europa generated an induced magnetic field in response to Jupiter's rotating magnetic field, the signature of an electrically conducting layer beneath the surface, responding to Jupiter's field the way a conductor responds to a changing magnetic environment. Salt water is electrically conducting. The simplest interpretation of the induced field was a liquid ocean beneath the ice, salty enough to carry electrical current, global in extent. The Galileo data placed the ice shell's thickness at somewhere between 10 and 30 kilometers, depending on the model. Beneath it, a liquid water ocean estimated at roughly 100 kilometers deep, containing, by some calculations, more liquid water than all of Earth's oceans combined, rests in direct contact with a rocky seafloor. That last detail matters enormously for the question of habitability. An ocean sealed between ice above and rock below, in contact with a rocky seafloor through which geothermal heat flows, is an ocean in which the chemistry of water-rock interaction proceeds continuously. On Earth, the places where seawater meets hot rock at hydrothermal vents on the ocean floor are among the most biologically productive environments on the planet, supporting entire ecosystems that derive their energy not from sunlight, but from the chemical energy released when hot. Mineral-rich water mixes with cooler seawater. The organisms at these vents, bacteria, archaea, tube worms, crabs, fish, live entirely on chemical energy, in permanent darkness, at pressures that would kill most surface life. They have no dependence on photosynthesis, and they have been there, in various forms, since the deep ocean hydrothermal vent system first established itself. Europa's ocean, in contact with its rocky seafloor, heated by the tidal flexing that Jupiter's gravity continuously applies to the Moon's interior, may have the same basic chemistry running in its depths. Kevin Hand at the Jet Propulsion Laboratory has spent much of his career working through the specific chemistry of Europa's ocean and the question of whether it could support life. His argument centers on chemical disequilibrium, the condition in which different parts of a system are at different chemical potentials, so that reactions can proceed and release energy. Life, fundamentally, is a system that exploits chemical disequilibrium. It takes in molecules at higher chemical potential and releases molecules at lower potential, capturing the energy difference in the process. Europa's ocean may be maintained in a state of chemical disequilibrium by two complementary processes: the oxidants produced at the ice surface, where Jupiter's radiation continuously bombards the ice and drives chemical reactions that produce hydrogen peroxide, oxygen, and other reactive compounds, and the reductants produced at the seafloor, where hot rock and water interact to produce hydrogen and hydrogen sulfide. If those oxidants can reach the ocean below, through cracks in the ice shell, through convective overturning of the ice, and mix with the reductants rising from the seafloor, the chemical gradient between them represents a potential energy source for biology. Hans' work has been careful to distinguish between the conditions that are necessary for life and the conditions that are sufficient for it. Europa's ocean may have liquid water, chemical energy, and the molecular building blocks of organic chemistry, all necessary conditions as far as current understanding goes. Whether those conditions are sufficient, whether life actually arose and persists in Europa's ocean, is a question that cannot be answered from Earth orbit or even from a spacecraft flying by. It requires either a lander capable of drilling through the ice shell and sampling the ocean directly, or the detection of biosignature compounds in material that the ocean itself delivers to the surface. The Europa Clipper mission, launched in October 2024, carries a suite of instruments designed to characterize the ocean's chemistry, map the ice shell's thickness and structure, and identify the most promising locations for a future lander. It is the most capable spacecraft ever sent to the outer solar system for the specific purpose of assessing habitability, and its data will take years to fully analyze. Carolyn Porco was the leader of the Cassini imaging team and had spent more than 2 decades working toward the Saturn mission before it arrived. Cassini entered Saturn orbit in July 2004 and began what would become a 13-year tour of the Saturnian system, imaging the planet, its rings, and its moons in detail that no previous mission had approached. In the early months of the orbital tour, the imaging team turned their cameras toward Enceladus, a small moon, roughly 500 kilometers in diameter, whose surface appeared startlingly bright and geologically young compared to the heavily cratered surfaces of Saturn's other mid-sized moons. The brightness indicated fresh ice, a surface that was being continuously renewed, suggesting some form of geological activity. In February 2005, as Cassini made a close flyby of the moon's south polar region, the cameras returned images that immediately became among the most discussed in the history of planetary exploration. From the south pole of Enceladus, rising in long plumes above the surface and extending hundreds of kilometers into space, were jets of material, water ice particles, vapor, and gas, erupting from a system of linear fractures near the pole that the imaging team quickly named the Tiger Stripes. The plumes were not expected. Nothing in the pre-Cassini understanding of Enceladus had predicted that this small, cold moon would be geologically active, let alone that it would be venting material from its interior into space at a rate sufficient to supply Saturn's E-ring, the broad, diffuse ring that Enceladus orbits within, and that, as Cassini later confirmed, is continuously replenished by the material the plumes eject. Porco and her team published their initial findings in Science in 2006, and the paper catalyzed a rapid reorganization of thinking about where in the solar system the conditions for life might be found. Enceladus was small, far from the Sun, and had been considered geologically dead. It turned out to be one of the most active geological objects in the solar system. The subsequent characterization of the plume material by Cassini's other instruments added depth to what the images had shown. The ion and neutral mass spectrometer detected water vapor, carbon dioxide, methane, and molecular hydrogen in the plume. The cosmic dust analyzer found silica nanoparticles, grains of silicon dioxide in a size range between 2 and 8 nanometers that formed specifically when hot water between 90 and 200 degrees Celsius dissolves silica from rock and then cools rapidly. The presence of silica nanoparticles in that size range is a direct indicator of hydrothermal activity. Hot water in contact with silicate rock at temperatures far above the freezing point of water, dissolving and reprecipitating minerals as it moves, combined with the detection of molecular hydrogen, which is produced in abundance when hot water reacts with olivine and other iron-magnesium silicates in a process called serpentinization. The plume chemistry built a compelling case that Enceladus harbors an active hydrothermal system at its seafloor, similar in its basic chemistry to the hydrothermal vent systems on Earth's ocean floor that support chemosynthetic ecosystems in permanent darkness. Christopher McKay at NASA Ames Research Center had been thinking about subsurface habitability long before the Cassini plume discoveries. His work on life in extreme environments, in the dry valleys of Antarctica, in permafrost, in highly saline lake ice, had established that microbial life's requirements were more flexible than standard definitions of habitability assumed, and that the subsurface environments of icy worlds might offer conditions as suitable for microbial life as anything on the surface of a rocky planet in a habitable zone. McKay's framing of the habitability question in terms of liquid water, energy sources, and chemical building blocks rather than in terms of surface temperature and atmospheric pressure was influential in shifting the field's attention toward the outer solar system's moons, and his work on the specific chemistry of Enceladus's plumes, calculating the energy available to methanogenic archaea from the hydrogen and carbon dioxide detected in the plumes, demonstrated that the chemical energy budget was sufficient to support a microbial ecosystem, at least in principle. Titan, Saturn's largest moon, occupies a different position in this landscape. Its surface temperature of approximately -179 degrees Celsius places it far below the range at which water can remain liquid, and its surface lakes and rivers are composed not of water but of liquid methane and ethane, hydrocarbons that remain liquid at Titan's temperatures the way water remains liquid at Earth's. The Huygens probe, released by Cassini and descending through Titan's atmosphere on January 14, 2005, transmitted data from the surface for approximately 72 minutes before its batteries were exhausted, the only direct surface measurement ever made in the outer solar system beyond the Moon. Huygens found a surface of water ice pebbles rounded by liquid flow, a thick, nitrogen-dominated atmosphere rich in complex organic compounds, and conditions that some astrobiologists have proposed might support a radically different form of life, one based on liquid methane as a solvent rather than liquid water. The proposal remains speculative and contested, but Titan's chemistry is unambiguously complex, continuously driven by ultraviolet radiation in the upper atmosphere and by the rain of liquid hydrocarbons onto the surface, and it has attracted sustained scientific attention precisely because it demonstrates that complex organic chemistry can operate in environments where water-based life is implausible. The broader significance of Europa, Enceladus, and Titan in the context of this episode's central question is that they revise the question itself. The habitable zone around a star is defined by the conditions for liquid water on a planetary surface, maintained by stellar energy. But tidal heating, The frictional warming produced in a moon's interior by the continuous gravitational kneading of a giant planet provides an energy source entirely independent of stellar distance. A moon in a resonant orbit around a gas giant can maintain liquid water in its interior indefinitely, regardless of how far it sits from the sun. The outer solar system's moons have been doing this, apparently, for billions of years. If any of them harbor life, that life has been isolated from the solar system's surface environments for the entire history of the solar system, evolving, if it evolved at all, in complete independence from anything that might have occurred on the inner planets. The possibility adds a layer of complexity to the already difficult question of how common life might be in the universe. If liquid water in contact with rock and chemical energy is sufficient for life to arise, and if tidal heating can provide those conditions around gas giants throughout a galaxy, then the relevant population of potentially habitable environments extends far beyond the habitable zone planets that the Drake equation and the Kepler mission statistics address. The moons of giant planets, which appear to be common, given that our own solar system has dozens of them, may represent a category of habitable environment as numerous as, or more numerous than, habitable zone, rocky planets. Whether that abundance translates into actual life depends on the one variable that neither chemistry nor physics nor spacecraft data has yet constrained: whether life, given the right conditions, actually arises. That question, the most important one, and the most completely open, is the one that the statistics of planetary frequency and the silence of the radio spectrum have been circling around for 60 years. Chapter 9. The Statistics of Silence. On the morning of April 8, 1960, a 26-meter radio telescope at the National Radio Astronomy Observatory in Greenbank, West Virginia, was pointed toward a star called Tau Ceti, 11 light-years from Earth. Frank Drake, a 29-year-old astronomer who had joined the observatory the previous year, had spent months quietly planning what he called Project Ozma, named after the queen of the fictional land of Oz, chosen because Oz was a place very far away, difficult to reach, and populated by strange beings. The project's premise was straightforward. If a technologically advanced civilization existed around a nearby star and was transmitting radio signals, a sufficiently sensitive radio telescope pointed at the right star at the right frequency might detect them. Drake chose a frequency of 1420 MHz, the emission frequency of neutral hydrogen, the most abundant element in the universe, on the reasoning that any civilization advanced enough to build radio telescopes would know this frequency and might consider it a natural beacon. He observed Tau Ceti and then Epsilon Eridani, another nearby sun-like star, for approximately 150 hours between April and July 1960. He detected nothing that could be attributed to an artificial signal. Project Ozma was the first systematic scientific attempt to detect evidence of extraterrestrial intelligence, and its result established the template that 60 years of subsequent searching would follow: careful, methodical observation across widening ranges of stars and frequencies and signal types, returning silence. The silence deserves to be considered carefully, because it is not the same thing as a negative result in the ordinary scientific sense. A negative result in most fields means that a hypothesis was tested and the predicted effect was not found, which constitutes evidence against the hypothesis. The silence of Ceti is different. It means that a search was conducted and nothing was found, but the search has covered an infinitesimal fraction of the parameter space, the number of stars, the range of frequencies, the range of signal types, the range of technological possibilities that a comprehensive search would need to cover. The absence of a detected signal is not evidence that no signals exist. It is evidence that no signals were found in the specific places, at the specific frequencies, during the specific observation windows that have been examined. The distinction matters because the conclusions drawn from the silence depend entirely on how much of the relevant space has actually been searched. And the honest answer is that very little of it has. What changed the statistical context of that silence was not the search itself, but the census. The Kepler Space Telescope, conceived by William Barucki at the NASA Ames Research Center and proposed to the agency repeatedly across a span of nearly 2 decades before receiving approval, launched on March 7, 2009, and spent the following 4 years staring continuously at a single field of roughly 150,000 stars in the constellation Cygnus. Its method was the transit photometry technique, measuring the brightness of each star in its field thousands of times and looking for the tiny, periodic dips in brightness that occur when a planet passes across the star's face as seen from Earth. The dips are small. An Earth-sized planet crossing a Sun-like star dims the star by roughly 84 parts per million, a signal detectable only because Kepler measured stellar brightnesses with a precision that had not previously been achieved from a space-based platform. Barucki had spent years in the 1980s and 1990s demonstrating that the photometric precision required for transit detection was technically achievable, running detector tests and simulations that established the method's feasibility before the mission existed to apply it. The Kepler mission's primary scientific result, accumulated across its 4-year primary mission and a subsequent extended mission called K2, was that planets are extraordinarily common. Around the 150,000 stars it observed, Kepler found thousands of planet candidates, of which the great majority were confirmed as genuine planets through follow-up observations. The confirmed exoplanet count from Kepler and subsequent missions exceeded 5,000 by 2022, representing a sample drawn from a tiny fraction of the Milky Way's stars. The demographic picture that emerged from this sample was striking in its consistency. Small planets, ranging from Earth-sized to Neptune-sized, are far more common than large planets, occurring around the majority of Sun-like stars and around an even higher fraction of the smaller, redder stars that constitute the most numerous stellar population in the galaxy. Gas giants like Jupiter are relatively rare. The solar system, with its large outer planets and small inner ones, is not a typical planetary architecture. It is one configuration among many, and not the most common one. The specific number that landed hardest in the habitability discussion came from a 2013 paper by Eric Pettigura, Andrew Howard, and Jeffrey Marcy, all then at the University of California, Berkeley. Their analysis of the Kepler data focused on the subset of Sun-like stars for which Kepler's observations were long enough and precise enough to detect Earth-sized planets in the habitable zone. A subset limited by the fact that detecting a planet in the habitable zone of a Sun-like star requires observing at least 3 transits, each separated by roughly a year, which means Kepler needed to operate for at least 3 years before the relevant statistics could be assembled. Pettigura, Howard, and Marcy estimated that approximately 22% of Sun-like stars in the Milky Way host an Earth-sized planet, between 0.75 and 1.5 times Earth's radius, in the habitable zone, 1 in 5. The Milky Way contains somewhere between 100 and 400 billion stars, of which roughly 10% are Sun-like in the relevant sense. 22% of those stars hosting a potentially habitable Earth-sized planet produces a number in the billions, somewhere around 8.8 billion candidate worlds in the Milky Way alone, by Pettigura and colleagues' estimate, before any consideration of the moons of giant planets or the subsurface oceans of icy bodies. 8.8 billion is a number that, stated plainly, ought to make the silence of SETI deeply puzzling. If even a small fraction of those worlds developed life, and if even a small fraction of those life-bearing worlds eventually produced technological civilizations, and if even a small fraction of those civilizations transmitted detectable signals into space, the Milky Way should be, by naive calculation, full of detectable signals. The fact that 60 years of searching has found none, or more precisely, has found no confirmed signals. There have been tantalizing detections, including one that will appear shortly, is either because the fractions are all very small, or because the search has not covered enough of the relevant space, or because the assumptions underlying the calculation are wrong in ways that matter. The nearest known exoplanet that sits within the habitable zone of its star is Proxima Centauri b, orbiting Proxima Centauri at a distance of approximately 4.24 light-years, the closest star system to the Sun. Proxima Centauri is a red dwarf, considerably smaller and dimmer than the Sun, and Proxima b orbits much closer to it than Earth orbits the Sun, placing it within the habitable zone despite the star's lower luminosity. Whether Proxima b is actually habitable is uncertain and contested. Red dwarf stars are prone to flares, intense bursts of ultraviolet and X-ray radiations that may be capable of stripping the atmospheres of closely orbiting planets, and a planet so close to its star is likely tidally locked, with one face permanently in daylight and the other in permanent darkness. Whether a tidally locked planet can maintain habitable conditions through atmospheric heat transport from the day side to the night side is a question that atmospheric models have not definitively resolved. Proxima b is the nearest potentially habitable world, and it is 11 years away at the speed of light, and we have almost no confirmed knowledge of its atmosphere, its surface, or its actual habitability. Radio telescopes have grown more sensitive and have surveyed larger regions of the sky since Project Ozma's 150 hours of observation. The SETI Institute, founded in 1984, has conducted systematic searches across a widening range of stars, frequencies, and signal types. The Breakthrough Listen program, funded beginning in 2015 with a 10-year, $100 million commitment, is conducting the most comprehensive search yet, using the Green Bank Telescope and the Parkes Telescope in Australia to observe the million nearest stars, the entire galactic plane, and the 100 nearest galaxies at a range of frequencies and with a sensitivity exceeding previous searches by orders of magnitude. As of the time of this chronicle, Breakthrough Listen has found no confirmed artificial signals. There has been one detection that has never been satisfactorily explained. On August 15, 1977, an astronomer named Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University, a survey telescope that scanned the sky continuously and printed its data on paper for manual review, when he noticed a sequence of signal intensity values that stood out from the background noise with a clarity that no other detection in Big Ear's history had matched. The signal lasted precisely 72 seconds, one full rotation of the telescope's antenna beam, and then vanished, never to recur despite repeated searches of the same region of sky. Amon circled the signal values on the printout and wrote "Wow" in the margin, and the notation became the signal's permanent name. The WOW signal had characteristics consistent with a narrowband radio transmission from a point source in the direction of the constellation Sagittarius. The correct frequency, the correct signal profile, the correct duration for a signal from a fixed point source as the Earth's rotation carried the telescope beam across it. What it lacked was recurrence. Despite dozens of subsequent observations of the same sky position with increasingly sensitive equipment, the signal has not been detected again. It remains, nearly 50 years later, the most anomalous single detection in the history of SETI, neither confirmed as artificial nor explained as natural. The demographic picture from Kepler and the silence from SETI exist in a tension that the Drake equation was designed to articulate but not resolve. The equation says, in essence, that the number of detectable civilizations in the galaxy is the product of several terms. How many stars form? How many have planets? How many planets are in habitable zones? What fraction develop life? What fraction develop intelligence? What fraction become technological? And how long technological civilizations persist? The first two terms are now well constrained by observation. Stars form, and planets are common. The third term, habitable zone occupancy, is better constrained than it was before Kepler, though the definition of habitable introduces enough uncertainty to make precise estimates difficult. The remaining terms, the biological and sociological ones, are entirely unconstrained by data. The silence of 60 years of SETI searching places an upper bound on the product of those terms, but the bound is loose enough to be consistent with a wide range of possibilities, from a galaxy teeming with technological civilizations that simply are not transmitting in ways we can detect, to a galaxy in which Earth is among the very few places where biological complexity has developed at all. The statistics of planetary frequency do not make the silence easier to interpret, they make it harder. If worlds capable of hosting life are numbered in the billions within our galaxy alone, and if the silence is real rather than a consequence of inadequate searching, something must be responsible for the gap between the number of candidate worlds and the number of detectable civilizations. The name given to whatever that something is, the Great Filter, contains within its two words an enormous range of possible answers, from the optimistic to the deeply uncomfortable. And the question of where in the sequence from world formation to technological civilization the filter operates is one that the subsequent chapters of this episode will attempt to lay out honestly, without pretending to a resolution that the evidence does not yet support. Chapter 10. What kills a biosphere? The Permian-Triassic extinction boundary is a line in the rock. It appears in limestone sequences on every continent and in the sediments of ancient ocean floors that have since been uplifted into mountain ranges. A thin horizon, often just a few centimeters thick, above which the fossil record changes so completely that a paleontologist can identify it without measurement tools. Below the line, the characteristic assemblage of Permian marine life, a diverse fauna that had been developing and elaborating for tens of millions of years. Its complexity, the accumulated product of evolutionary experimentation across an enormous span of geological time. Above the line, almost nothing. The marine fauna above the Permian-Triassic boundary is so impoverished compared to what lay below it that early geologists who encountered the sequence initially doubted their own stratigraphy. Approximately 96% of marine species disappeared. On land, estimates suggest somewhere between 70 and 75% of vertebrate species were eliminated. The event, which occurred approximately 252 million years ago, is the largest mass extinction in Earth's history, larger than the asteroid impact that ended the dinosaurs, larger than the late Ordovician glaciation, larger than any of the other extinction events that punctuate the fossil record. Recovery took between 5 and 10 million years, and some lineages never recovered at all. The mechanism responsible for the Permian-Triassic extinction was not a single event, but a convergence of processes, triggered by one of the largest volcanic episodes in Earth's history, the Siberian Traps, a vast outpouring of basaltic lava covering approximately 7 million square kilometers of what is now Siberia, produced by a mantle plume that reached the crust approximately 252 million years ago, erupted over a period of perhaps 1 to 2 million years, releasing quantities of carbon dioxide, sulfur dioxide, and other volatiles that drove a rapid and severe greenhouse warming of the global climate. The carbon dioxide from the eruptions acidified the oceans as it dissolved into seawater, interfering with the ability of carbonate-shelled organisms to build and maintain their shells. The warming drove ocean stratification, reducing the mixing of oxygenated surface water with deeper water and producing widespread anoxia, oxygen depletion, in the ocean interior. Hydrogen sulfide, produced by anaerobic bacteria in anoxic bottom waters, diffused upward into shallower water and eventually into the atmosphere in concentrations sufficient to be directly toxic to many organisms. The combination of warming, acidification, anoxia, and hydrogen sulfide toxicity operated simultaneously across the global ocean and across terrestrial environments, and the cumulative effect was a collapse of biological diversity at a scale that the planet has never matched before or since. The geological record of the recovery is in some ways more instructive than the record of the extinction itself. Peter Ward at the University of Washington, whose work on mass extinction patterns spans more than 3 decades, has characterized the Permian-Triassic recovery as one of the slowest and most uneven in the geological record. Not a gradual return toward pre-extinction diversity, but a prolonged period of ecological simplification, dominated by opportunistic generalist species, in which the complex ecosystems that had characterized the Permian took millions of years to reassemble. Ward's framing of mass extinctions as not merely episodic setbacks, but as genuine resets of biological complexity, events that eliminate the accumulated evolutionary experimentation of tens of millions of years and force the biosphere to rebuild from a simpler starting point, has influenced how planetary scientists think about the relationship between geological stability and biological complexity. A biosphere that has been through a Permian-Triassic scale extinction is not simply a damaged version of what it was before. It is a different system, one that must redevelop its complexity along whatever evolutionary pathways remain available to the survivors. Luis Alvarez was a Nobel Prize-winning experimental physicist who had spent his career in particle physics and had no particular interest in paleontology until, in the late 1970s, his son Walter, a geologist at the University of California, Berkeley, showed him a puzzling feature in a limestone sequence near Gubbio, in the Apennine Mountains of central Italy. The Gubbio sequence spans the Cretaceous-Paleogene boundary, the moment approximately 66 million years ago at which the non-avian dinosaurs and roughly 3/4 of all species on Earth disappeared. And Walter had been studying the thin clay layer that marks the boundary for years, trying to understand what it represented. The clay layer was geochemically unusual, enriched in certain elements at concentrations far above background levels, and Walter thought that measuring the deposition rate of the layer might help constrain the duration of the extinction event. Luis recognized that the element they needed to measure was iridium, a platinum group metal extremely rare in Earth's crust but present in meteoritic material at concentrations roughly 10,000 times higher than in terrestrial rock. The idea was that cosmic dust settles from space at a roughly constant rate, so measuring the iridium concentration in the clay layer would indicate how long the clay had taken to accumulate. The measurement, carried out by Frank Asaro and Helen Michel at the Lawrence Berkeley Laboratory, returned a result that neither Alvarez had anticipated. The iridium concentration in the Gubbio boundary clay was not slightly elevated. It was approximately 30 times higher than background levels in the surrounding limestone. The anomaly was not a measurement artifact. It was confirmed in the Gubbio samples and then in boundary samples from Denmark and New Zealand, establishing that the iridium enrichment was a global phenomenon, present simultaneously in sedimentary sequences on opposite sides of the planet. Luis Alvarez concluded that the only plausible source for a globally distributed iridium anomaly was extraterrestrial, a large asteroid or comet impact that had vaporized the impacting body and distributed its material as fine particles through the global atmosphere, which then settled slowly and uniformly over months or years onto the ocean floor and the land surface worldwide. The Alvarez team published their hypothesis in Science in 1980. The hypothesis was controversial for a decade. Paleontologists resisted what they perceived as a physicist imposing a simple catastrophic explanation onto a complex biological record, and several lines of fossil evidence were initially interpreted as showing a more gradual extinction than a sudden impact would predict. The controversy shifted in 1991 when the Chicxulub crater, a buried impact structure beneath the Yucatan Peninsula and the Gulf of Mexico floor, approximately 180 to 200 kilometers in diameter, was confirmed as the impact site through a combination of shocked quartz, tektites, and the anomalous iridium layer that correlate in time and geography. The Chicxulub impactor, estimated at 10 to 15 kilometers in diameter, struck the shallow carbonate platform of the proto-Gulf of Mexico and released energy equivalent to roughly 1 billion nuclear weapons, igniting global wildfires, ejecting enough material into the stratosphere to block sunlight for months to years, and triggering a collapse of photosynthesis that propagated through the food web from the bottom up. The impact winter, the extended period of reduced sunlight and sharply lowered temperatures that followed, was the proximate cause of the extinction of the non-avian dinosaurs and the elimination of the majority of species alive at the time. The Kapig extinction is the most thoroughly studied mass extinction in Earth's history, and the investigation of its cause, from Walter Alvarez's field observations in the Apennines to the confirmation of the Chicxulub crater and the detailed modeling of impact winter dynamics, represents one of the most productive scientific detective stories of the 20th century. What the investigation established, beyond the specific mechanism of the KPG event, was that large impact events are a normal feature of planetary history, occurring at irregular intervals but with a long-term frequency that can be estimated from the cratering record on the Moon and from the population of near-Earth asteroids currently tracked by survey telescopes. The solar system contains a reservoir of impactors, asteroids and comets in orbits that periodically cross the inner solar system, and the probability of a civilization-threatening impact on Earth within any given million-year period is not negligible. The Chicxulub event was not anomalous. It was simply the most recent large impact in a long series, and the series has not ended. Lynn Margulis spent much of her career arguing for a view of life's history that was less linear and less inevitable than the standard evolutionary narrative assumed. Her endosymbiosis hypothesis, developed through the 1960s and published in full in a 1967 paper that was rejected by 15 journals before appearing in the Journal of Theoretical Biology, proposed that the eukaryotic cell, the cell type that contains a membrane-bound nucleus and is the building block of all complex multicellular life, was not a gradual evolutionary development from prokaryotic ancestors, but a specific merger, a prokaryotic host cell that had engulfed and then retained in a mutually dependent relationship other prokaryotic cells that became the mitochondria and chloroplasts of the resulting eukaryote. The evidence for the hypothesis: the double membranes of mitochondria and chloroplasts, their distinct ribosomes, their separate circular DNA, their reproduction by binary fission independent of the cell cycle, is now considered conclusive, and endosymbiosis is the accepted explanation for the origin of eukaryotic organelles. But Margulis's broader point, which extended beyond the specific endosymbiosis mechanism, was that the major transitions in life's complexity were not gradual accumulations of small steps, but rare, specific, contingent events, mergers, transfers, symbioses that could easily not have happened. and that life's current complexity therefore could not be extrapolated backward as though it were inevitable. The relevance of Margulis's framing to the question of dead worlds is that it introduces contingency at precisely the level where the habitability discussion most needs it. A planet in the habitable zone with liquid water and the right chemistry is a candidate for life. Whether that candidate world develops microbial life, and whether that microbial life makes the transition to eukaryotic complexity, and whether that eukaryotic complexity eventually produces multicellular organisms, and whether multicellular organisms eventually produce the nervous system complexity associated with intelligence, are not steps that follow automatically from one another. Each transition was, on Earth, a specific event that required specific conditions and that occurred once, as far as the fossil record shows, in a specific geological context. The Cambrian explosion, which produced the basic body plans of virtually all animal phyla in a geologically brief window beginning approximately 538 million years ago, was itself a contingent event dependent on specific geochemical conditions, specific ecological pressures, and specific genomic innovations that occurred in a specific order. Had any of the preceding snowball glaciations succeeded in eliminating all surface life rather than merely devastating it, the Cambrian explosion would not have happened, and the subsequent history of life on Earth would have been nothing, or something entirely different. The mechanisms that kill biospheres operate at different timescales and through different pathways, but they share a common structure. They remove or severely reduce the conditions that allowed biological complexity to develop, and the recovery from their damage, if it occurs, requires the reconstruction of complexity from simpler components through processes that are neither rapid nor guaranteed. A Permian-Triassic scale volcanic episode on any planet with a biosphere would produce the same basic sequence: rapid climate disruption, ocean chemistry alteration, mass extinction, and a prolonged period of ecological simplification, followed by slow recovery. A Chicxulub-scale impact would produce impact winter, photosynthetic collapse, and food web destruction propagating from the base upward. A runaway greenhouse would produce atmospheric water loss, surface sterilization, and the elimination of the carbon cycle that moderate climates require. A magnetic field collapse, followed by atmospheric stripping, would produce gradual desiccation and surface sterilization over geological time. Each pathway ends in the same place: a world that was once biologically active and is no longer, its surface preserving the chemical and mineralogical record of what it had been before the mechanism that killed it ran to completion. Whether any of those mechanisms are operating right now on worlds around other stars, whether there are planets in the Milky Way whose biospheres are currently being ended by volcanic outgassing, or impact events, or runaway greenhouse transitions, or magnetic field decay, is not a question that can be answered with current instruments. What current instruments can address is the statistical framework for how often those mechanisms operate, and what fraction of the worlds that begin with the conditions for life might eventually be ended by one or more of them. That framework, built from the equations and estimates and arguments of a group of scientists who have spent decades trying to quantify the gap between planetary frequency and biological complexity, is the subject of the chapters that follow. Chapter 11: The Drake Equation and its Honest Failures. In November 1961, 11 scientists gathered at the National Radio Astronomy Observatory in Green Bank, West Virginia, for a meeting that had no official name, no institutional sponsor beyond the observatory itself, and no agenda in the conventional sense. The gathering had been organized by Frank Drake, who was then 31 years old and had completed Project Ozma 18 months earlier. Drake had invited a small group of researchers whose work touched, from different directions on the question of whether intelligent life existed elsewhere in the universe. Among them Carl Sagan, then a 27-year-old postdoctoral researcher, the neuroscientist John Lilly, who had been studying dolphin communication and whose presence reflected the meeting's interest in intelligence as a general phenomenon rather than a specifically human one. The radio astronomer Philip Morrison, who had co-authored a foundational 1959 paper in Nature proposing that radio waves were the logical medium for interstellar communication, and the biochemist Melvin Calvin, who received word during the meeting that he had been awarded the Nobel Prize in Chemistry and took the congratulatory phone call between sessions without particular disruption to the proceedings. The meeting lasted 2 days. It produced no formal publication. What it produced, instead, was a framework that has structured the question of extraterrestrial intelligence ever since. Drake had faced a practical problem in organizing the meeting. The question of whether intelligent life existed elsewhere in the universe was so broad, and the relevant considerations so varied. Stellar astronomy, planetary science, chemistry, biology, neuroscience, sociology, engineering, that a 2-day discussion among 11 people could easily have dispersed into unconnected monologues rather than converging on anything useful. He needed a way to organize the conversation, a structure that would ensure all the relevant factors were considered in relation to each other rather than in isolation. The night before the meeting, working through the problem, Drake wrote an equation on a blackboard. The equation expressed the number of technologically communicating civilizations currently active in the Milky Way as the product of a series of terms, each representing one factor in the chain from star formation to detectable civilization: the rate at which stars form in the galaxy, the fraction of those stars with planetary systems, the number of habitable planets per planetary system, the fraction of habitable planets on which life actually arises, the fraction of intelligent species that develop technology and choose to communicate, and the average lifespan of a communicating civilization. Drake did not present the equation as a formula for calculating a known answer. He presented it as an agenda, a way of ensuring that the meeting worked through each relevant factor in turn and arrived at whatever collective estimate the assembled expertise could support. The equation is written in the notation Drake established as n equals r star multiplied by f me multiplied by ne multiplied by fl multiplied by fi multiplied by fc multiplied by l. Each term beyond the first two has, in the 60 years since Drake wrote it on the blackboard in Green Bank, resisted quantification with increasing stubbornness. The rate at which sun-like stars form in the Milky Way, the first term, is now measured with reasonable precision from stellar surveys, approximately 1 to 3 sun-like stars per year across the galaxy. The fraction of those stars with planetary systems, the second term, has been transformed by the Kepler mission from a guess into a measurement. Close to 1, meaning nearly all stars have planets. The number of habitable planets per system, the third term, is better constrained than it was before Kepler, with estimates for Earth-sized planets in habitable zones around sun-like stars running at roughly 1 in 5 systems by Pettigura and colleagues' 2013 calculation. These first 3 terms, the astronomical ones, have moved from speculation to data over the course of Drake's lifetime. The remaining terms have not. The fraction of habitable planets on which life actually arises, FLER, is the first term for which no data exists beyond a single data point. Earth. Earth developed life relatively quickly by geological standards. The earliest evidence for microbial life dates to approximately 3.7 to 4.1 billion years ago, within a few 100 million years of the planet's surface cooling enough for liquid water to persist, which some researchers interpret as evidence that life arises readily when conditions are suitable. since a process that requires billions of years of waiting would not have produced life so early on a planet whose total lifespan is 10 billion years. Others argue that a single data point cannot support statistical inference in any direction, and that the early appearance of life on Earth tells us nothing reliable about F as a universal constant. Both positions are defensible. Neither is constrained by anything beyond the single case we have observed. The fraction of life-bearing worlds on which intelligence develops, Phi, introduces a further layer of uncertainty. Intelligence, in the sense relevant to the Drake equation, means the development of a nervous system complex enough to produce abstract reasoning, tool use, language, and eventually technology. On Earth, complex nervous systems developed multiple times independently, in vertebrates, in cephalopods, in some arthropods, but the specific combination of capacities associated with human intelligence appears to have arisen only once, in a single lineage, after roughly 3.5 billion years of biological evolution. Whether this reflects the extreme difficulty of the transition, or the particular contingency of the evolutionary pressures that produced it, or simply the sample size problem of observing one planet's history, is genuinely unknown. The paleontologist and evolutionary biologist Stephen Jay Gould spent much of his career arguing that intelligence was not an inevitable outcome of evolution, but an accidental one, that replaying the tape of life on Earth would, with overwhelming probability, produce something entirely different from human intelligence, because the evolutionary transitions that led to it were contingent on specific ecological and geological events that could easily have unfolded differently. Simon Conway Morris at the University of Cambridge has argued that convergent evolution, the independent development of similar solutions to similar problems, suggests that intelligence is an attractor in evolutionary space, a solution that evolution tends toward given sufficient time and complexity. The disagreement has not been resolved. Jill Tarter joined the SETI Institute shortly after its founding in 1984 and spent the following 3 decades as its most visible scientific figure, directing the Institute's research programs and serving as the public face of the systematic search for extraterrestrial intelligence. Her scientific work focused on developing search strategies, deciding which stars to observe, at what frequencies, with what sensitivity, looking for what kinds of signals, and on building the computational infrastructure needed to analyze the enormous data volumes that sensitive radio searches produce. Tarter's contribution to the field was organizational and methodological as much as it was observational. She understood that the search, to be scientifically credible, needed to be systematic, documented, and subject to the same standards of evidence as any other empirical science, rather than dependent on the charisma or intuitions of individual observers. The SETI Institute she helped build institutionalized that rigor, and the Breakthrough Listen program that followed in 2015 extended it to a scale and sensitivity that no previous search had approached. The WOW signal arrived at the Big Ear radio telescope on August 15, 1977, in a form that nobody at the observatory noticed until Jerry Amon reviewed the printed data several days later. Big Ear operated as a survey instrument, scanning the sky continuously and printing its intensity measurements as a sequence of alphanumeric characters, numbers from 0 to 9 representing increasing signal intensity, and letters from A onward for intensities above 10 times background. The normal output was an undifferentiated sequence of low numbers, the background noise of the sky. On the printout from August 15th, in the data corresponding to a source in the direction of the constellation Sagittarius, Amon found the sequence 6 EQ Gay 5, a rapid rise and fall in intensity that peaked at the character U, representing a signal intensity approximately 30 times above the background noise. with a duration of exactly 72 seconds. The duration matched precisely what would be expected from a narrowband point source, a source of effectively zero angular diameter, as the Earth's rotation carried Big Ear's fixed antenna beam across it. A signal from a fixed location in the sky, whether a star or something near one, would produce exactly that profile: a smooth rise as the beam approached, a peak as the beam centered, and a smooth fall as it moved away, lasting one full beam-width transit of 72 seconds. Eamon circled the sequence in red pen and wrote "Wow" beside it, and the notation became permanent. The signal has not been detected again. Dozens of subsequent observations of the same sky position, including observations with more sensitive telescopes than Big Ear, have returned nothing. The region of sky in question contains two sun-like stars, 2 mass 19 to 80 1982 2640123 and 2 mass 19290190 263055, at distances of roughly 1,800 and 1,010 light-years respectively. A detail noted in a 2016 analysis by Antonio Paris that also proposed a different explanation for the signal: a hydrogen cloud associated with comets in the inner solar system. The cometary hypothesis has been contested. Subsequent attempts to replicate the signal from cometary sources have not convincingly reproduced the WOW signal's characteristics. The signal remains unexplained, and the honest characterization of it is that it is an anomaly, a single detection, unrepeated, consistent with but not confirmed as an artificial narrowband transmission from a point source in the direction of Sagittarius. The longevity term, L, the average lifespan of a communicating technological civilization, is the Drake equation's most uncomfortable variable, and the one whose value most determines whether n is large or small. If technological civilizations persist for millions of years after developing radio communication, L is large, and n, the number currently active in the Milky Way, is correspondingly large, which makes the silence of SETI difficult to explain. If technological civilizations persist for only a few thousand years before destroying themselves through war, environmental collapse, or technological accident, L is small, and n might be very small even if intelligent life is common, perhaps so small that the nearest civilization to us is tens of thousands of light-years away, and the probability of any two civilizations being active simultaneously within communication range of each other is negligible. The longevity term was what made the Green Bank Conference participants, who gathered during the Cold War at a moment when nuclear annihilation seemed a plausible near-term possibility, most uncomfortable. Carl Sagan, who thought about the longevity term more publicly than almost anyone else associated with SETI, argued that the Drake equation's L variable was essentially a question about whether technological civilizations could survive their own technology, and that the answer to that question was the most important one humanity faced, not merely for the SETI calculation, but for its own continued existence. The Green Bank Conference estimates for N ranged from 1,000 to 100,000 civilizations currently active in the Milky Way, depending on the values each participant assigned to the uncertain terms. The range spanning 5 orders of magnitude was itself the result, not a failure of the exercise, but its honest product. The equation's value was never in producing a number. It was in making explicit which factors mattered and how uncertain each one was. In the 60 years since Drake wrote it on the blackboard, the astronomical terms have narrowed considerably, while the biological and sociological terms have not narrowed at all. The equation stands today in roughly the same epistemic position it occupied in 1961, a framework that precisely locates the boundaries of human ignorance, with the astronomical boundary pushed back considerably and the biological boundary unmoved. What the Drake equation cannot accommodate, what no equation built from current knowledge can accommodate, is the possibility that the transition from chemistry to biology is not a probabilistic event that occurs with some regular frequency given the right conditions, but a specific, contingent, historically particular event that may have occurred only once, or a handful of times, in the observable universe. If the origin of life required not merely the right conditions, but a specific sequence of chemical accidents that is genuinely improbable rather than merely uncommon, F. Lee could be so small that Earth is one of the only living worlds in the Milky Way, or in the local group, or in the observable universe. The equation has a term for this possibility, FLER, but the term cannot be assigned a value, and a term that cannot be assigned a value does not constrain the equation's output. The silence of SETI is consistent with this possibility. It is also consistent with the opposite possibility, and it is, as yet, consistent with almost everything in between, which is the honest answer to a question that the science has been asking seriously for 60 years and has not yet answered at all. Chapter 12: Rare Earth and its Critics. Peter Ward had spent decades studying mass extinctions, reading the fossil record of what had been lost, calculating the timescales of recovery, thinking carefully about what the pattern of biological catastrophe in Earth's history implied about the conditions under which complex life could persist. Don Brownlee had spent an equivalent span studying cosmic dust, comets, and the chemical composition of the early solar system, the material that planets are built from, and the environments in which they form. When the two University of Washington scientists began collaborating in the late 1990s on a book that would synthesize their different perspectives into a single argument about the rarity of complex life, they were not working from a shared conclusion, but from a shared unease, a sense that the optimistic assumptions embedded in most SETI-adjacent thinking about the prevalence of intelligent life were not adequately grounded in what planetary science, geology, and paleontology had actually established. The book they produced, published in 2000 under the title Rare Earth: Why Complex Life is Uncommon in the Universe, was received as a provocation, a corrective, and, depending on the reader, either a necessary grounding of an over-optimistic field or an overcorrection that imposed Earth's specific history as a universal template. The central argument of Rare Earth was built from an inventory of conditions. Ward and Brownlee did not argue that microbial life was rare. They explicitly acknowledged that simple single-celled life might be widespread in the universe, carried by the basic chemistry of carbon and water that appears to be common throughout the cosmos. Their argument was specifically about complex multicellular life, animals, in the biological sense, and the claim was that the conditions required for complex life to develop and persist were far more restrictive than the conditions required for microbial life, and that those more restrictive conditions were met on Earth through a combination of factors that, considered individually, were each plausible but whose simultaneous occurrence was statistically improbable. The Moon was the first condition Ward and Brownlee emphasized. Earth's unusually large moon, formed through the giant impact of Theia approximately 4.5 billion years ago, stabilizes Earth's axial tilt within a narrow range, preventing the wild oscillations that Mars undergoes in the absence of a comparable satellite. Without that stability, Earth's climate would vary more dramatically over geological time, potentially driving glaciations and warming events severe enough to prevent the development of the complex ecosystems that multicellular life requires. The Moon is not merely a feature of Earth's sky. It is, in Ward and Brownlee's argument, a component of Earth's climate regulation system. Jupiter was the second condition. Jupiter's mass, 318 times Earth's, gives it a gravitational influence that shapes the architecture of the entire solar system. And one consequence of that influence is that Jupiter acts as a partial shield for the inner solar system against cometary and asteroid bombardment. Objects falling into the inner solar system from the outer regions are frequently captured or deflected by Jupiter's gravity before reaching the terrestrial planets. Without Jupiter, the impact rate on Earth over geological time would be considerably higher, and the frequency of mass extinction events like the KPG impact that Ward had spent years studying, would correspondingly increase. A planet experiencing Chicxulub-scale impacts every 100 million years rather than every few 100 million years would have its biosphere reset more frequently, potentially preventing the accumulation of biological complexity that required stable conditions over hundreds of millions of years to develop. Jupiter's protective function is not absolute. The late heavy bombardment occurred despite Jupiter's presence, and some analyses suggest Jupiter may direct as many impactors toward Earth as it deflects. But the broad point that the presence or absence of a large outer planet affects the inner system's impact environment is well supported. The third condition was galactic position. Ward and Brownlee incorporated the galactic habitable zone concept developed by Guillermo Gonzalez and argued that Earth's location in the Orion Arm, approximately 27,000 light-years from the galactic center, placed it in a region of the Milky Way that was chemically enriched enough to build rocky planets with the right elemental abundances, while being far enough from the galactic center to avoid the intense radiation environment, supernovae, gamma-ray bursts, the active galactic nucleus that would sterilize planetary surfaces in the inner galaxy. Stars near the galactic center are metal-rich and surrounded by dense stellar populations. They are also bathed in radiation levels that some models suggest would strip ozone layers and damage the DNA of surface organisms on a timescale too short for complex life to develop. Stars in the galactic outskirts are spared that radiation but are so metal-poor that the rocky planets they form are likely too small and too chemically impoverished to support the plate tectonics and geochemical cycling that Earth's long-term habitability has depended on. The galactic habitable zone, the intermediate band where conditions are neither too violent nor too chemically sparse, occupies a fraction of the Milky Way's total stellar population, and Earth sits within it. The argument compounded. Take the fraction of stars in the galactic habitable zone, multiply by the fraction with a Jupiter analog planet in the right orbit, multiply by the fraction with an Earth-sized planet in the habitable zone stabilized by a large moon formed through a giant impact, multiply by the fraction with active plate tectonics driving the carbon-silicate cycle, multiply by the fraction that avoided a sterilizing extinction event during the critical window when complex life was developing, and the resulting number, Ward and Brownlee suggested, was very small, possibly so small that complex multicellular life was genuinely rare in the galaxy, perhaps even unique to Earth in the Milky Way, or close to it. The universe might be full of worlds harboring microbial life, or the chemical precursors of life, or the ruins of worlds where simple life had briefly developed and then been eliminated by one of the mechanisms this episode has surveyed. What it might not be full of was anything more complex than bacteria, any world that had made it through the full sequence of contingencies that Earth had navigated and arrived at the level of biological organization that produces nervous systems, behavior, and eventually the kind of intelligence that wonders about its own rarity. The critics arrived quickly and with specific objections. Charles Lineweaver at the Australian National University, whose work on the galactic habitable zone produced the 2004 analysis estimating that roughly 9% of Milky Way stars had formed in the right place and at the right time to host potentially habitable planets, argued that Ward and Brownlee had set the conditions too specifically. that the argument for each individual condition rested on Earth's history as a template in ways that were not fully justified. The Moon's stabilizing role, for example, depends on how much axial tilt variation is actually lethal to complex life, which is an assumption rather than a measured constraint. Planets without large moons, but with different atmospheric masses or different orbital configurations, might have different but equally stable climate regimes. Jupiter's protective function, as noted, is contested even for Earth. The question of whether Jupiter is net beneficial or net harmful to the inner solar system's impact environment has not been definitively resolved. Each condition in the rare Earth argument was, individually, a reasonable hypothesis. The question was whether multiplying reasonable hypotheses together produced a reliable estimate or an accumulation of unverified assumptions. Milan Ćirković at the Astronomical Observatory of Belgrade brought a different critical perspective, grounded in the philosophy of the Fermi paradox. Ćirković's scholarship engaged with the logical structure of arguments about extraterrestrial intelligence with unusual rigor, and his critique of rare Earth-style arguments focused on what he called anthropic bias, the difficulty of reasoning about the probability of one's own existence from within the single instance of it that one has access to. Any observer capable of asking whether complex life is rare must, by definition, be an instance of complex life, which means the observation of one's own existence cannot serve as evidence about the general frequency of complex life without careful correction for the fact that only living observers can make observations. The argument is subtle and has a long history in philosophy of science, but its practical implication for the rare Earth debate is that Earth's specific history, the Moon, Jupiter, galactic position, plate tectonics, cannot be straightforwardly used to argue that complex life is rare, because we can only observe Earth's history from the perspective of an observer who exists because Earth's history unfolded as it did. The conditions that produced us are not necessarily improbable in an absolute sense. They are merely the conditions that produced us, which is a tautology masquerading as an argument. David Grinspoon, whose work on planetary habitability and the long-term evolution of planetary environments has spanned several decades and several books, argued against the rare Earth hypothesis from a different angle, not by contesting the specific conditions Ward and Brownlee identified, but by questioning whether those conditions were as stringent as the argument assumed. Plate tectonics, often cited as a critical component of Earth's long-term habitability through its role in the carbon-silicate cycle, may not be the only geological mechanism capable of driving that cycle. Volcanic outgassing and crustal resurfacing without full plate tectonics might serve similar functions in different planetary configurations. The specific thickness and composition of Earth's crust, the specific ratio of land to ocean, the specific rate of plate subduction. These are the conditions that drove Earth's carbon cycle, but other conditions might drive an equivalent cycle through different mechanisms. Life, once established, also modifies the planetary environment in ways that may expand the range of conditions under which it can persist. The Great Oxidation Event was driven by biology, and the resulting oxygenated atmosphere opened up metabolic pathways unavailable in a reducing atmosphere, potentially making the biosphere more robust against future perturbations. The debate between the rare Earth hypothesis and its critics has not resolved into a consensus in the 2 decades since Ward and Brownlee's book appeared, and the honest assessment is that the evidence does not yet compel either conclusion. What the debate has produced is a clearer articulation of the specific uncertainties, which conditions are genuinely necessary for complex life and which are merely sufficient for the Earth-specific history that produced us. How much weight to give each factor in a probabilistic argument that compounds many uncertain estimates, and how to reason carefully about probability and contingency when the sample size is 1. These are not merely scientific questions. They are philosophical ones about the nature of inference from limited data, and the answers depend on methodological commitments, about how to handle anthropic selection effects, about how much weight to give theoretical arguments versus empirical constraints that the scientific community has not uniformly adopted. Ward himself, in subsequent work co-authored with Joe Kirschvink, the same Kirschvink who had coined the snowball Earth concept, revised and extended some of the arguments from rare Earth in a 2015 book titled A New History of Life. The revision was in some ways a softening. Ward and Kirschvink acknowledged that the Cambrian explosion and the major transitions in animal evolution were more deeply connected to geochemical events. The snowball glaciations, the oxygenation of the deep ocean, the specific chemistry of the Ediacaran oceans, than the original rare earth argument had emphasized, and that these connections suggested a more contingent and event-driven account of complex life's development than a simple multiplication of independent probabilities would capture. The history of life on Earth was not the product of a set of background conditions, each independently necessary, but of a specific sequence of events, each building on what preceded it, in ways that made the outcome dependent on the particular path rather than on the general properties of the environment. That path dependence does not make complex life impossible elsewhere. It makes it a historical question rather than a statistical one, which is in some respects a harder problem. What rare earth and its critics together accomplished, regardless of which side of the argument one finds more speculative, was to force the habitability discussion to engage seriously with the specific mechanisms and timescales involved in the development of complex life, rather than treating the question as primarily one of planetary frequency. The Kepler mission could establish how many Earth-sized planets existed in habitable zones. It could not establish how many of those planets had the specific geological, chemical, and dynamical properties that Ward and Brownlee argued were required for complex life to develop. Those properties require a different kind of investigation, one that examines planetary atmospheres, geological activity, orbital architectures, and stellar environments in detail, and attempts to determine which of those properties are genuinely necessary and which are merely the particular features of the one example we have. That investigation is now underway, with tools that did not exist when Ward and Brownlee were writing, and the data it produces will determine whether the universe is full of dead worlds in the microbial sense alone, or in the deeper sense that complex life, life that builds nervous systems and eventually asks questions, is itself the rarest thing the universe has managed to produce. Chapter 13. What the silence costs us to hear. Across the 14 billion years that the universe has been forming stars and planets, the conditions for liquid water have existed, by current estimates, around billions of worlds in the Milky Way alone. Some of those worlds formed early, in the galaxy's first few billion years, when the heavy elements needed for rocky planet construction had already been seeded by the first generation of massive stars. Some formed recently, around stars younger than the Sun, on planets whose surfaces may still be geologically active in ways that Earth's will not be in another 5 billion years. The temporal spread of potentially habitable worlds across galactic history means that if life arises with any regularity given the right conditions, the galaxy has had an enormous amount of time and an enormous number of venues in which to produce it. The question that the silence forces is not whether the conditions have existed. They have. The question is what has happened to the worlds that possess them, and why the silence that greets every attempt to detect the products of those worlds is as complete as it has remained across 6 decades of searching. The James Webb Space Telescope, launched on December 25, 2021, and placed at the second Lagrange point 1.5 million kilometers from Earth, represents the most capable astronomical instrument ever built for the specific purpose of examining the atmospheres of worlds around other stars. Its primary mirror, 6.5 meters across and composed of 18 hexagonal gold-coated beryllium segments, collects infrared light with a sensitivity that allows it to detect the atmospheric signatures of planets transiting their host stars. The specific wavelengths absorbed by atmospheric molecules as the planet's atmosphere filters the starlight passing through its edge during a transit. The technique, called transmission spectroscopy, produces a spectrum in which the depths of specific absorption features correspond to the concentrations of specific molecules in the planet's atmosphere. Water vapor, carbon dioxide, methane, oxygen, ozone, each leaves a characteristic fingerprint in the spectrum, and the combination of molecules present in a planetary atmosphere carries information about the chemistry occurring at the planet's surface and in its atmosphere that no other currently available technique can access from Earth's vicinity. Sarah Seeger at the Massachusetts Institute of Technology has spent much of her career thinking carefully about what those atmospheric fingerprints could reveal, and specifically about what combination of atmospheric molecules would constitute a biosignature, a chemical signal that biological processes produce and that no known non-biological process could maintain. Her work has moved the biosignature concept from a general intuition, life produces oxygen, so look for oxygen, toward a more rigorous framework grounded in thermodynamic disequilibrium. The core of Seeger's argument is that life's distinguishing chemical characteristic is not the production of any single molecule, but the maintenance of a set of molecules that, in the absence of a continuous biological source, would react with each other and disappear on timescales short compared to the age of a planet. Oxygen and methane coexisting in a planetary atmosphere is the canonical example. In the presence of oxygen, methane is oxidized to carbon dioxide and water on a timescale of roughly 10,000 years. Meaning that an atmosphere containing significant quantities of both gases simultaneously must have a continuous source replenishing both. No known geological process does this. Photosynthesis produces oxygen, methanogenic archaea produce methane, and the coexistence of both in Earth's atmosphere is a direct consequence of the biological productivity of both groups of organisms, operating simultaneously. The thermodynamic disequilibrium between them is, in Seeger's framing, the chemical signal of a living planet, not because life is the only conceivable source, but because it is the only known source capable of maintaining the disequilibrium indefinitely. In 2013, Seeger published what some researchers have called the Seeger equation, a reformulation of the Drake equation specifically adapted to the search for biosignatures in exoplanet atmospheres, replacing the sociological terms about intelligence and communication with terms about the detectability of atmospheric chemical signals. The reformulation reflected a shift in how the search for life was being conceived, not primarily as a search for radio signals from technological civilizations, but as a search for the chemical signatures of biology in planetary atmospheres, detectable with instruments like the Webb telescope, regardless of whether the life producing those signatures was intelligent, multicellular, or even aware of its own existence. A planet covered in photosynthetic bacteria and methanogenic archaea, with no nervous systems more complex than those of a flatworm, would produce the oxygen-methane disequilibrium signal as clearly as a planet with cities and radio transmitters. The search for biosignatures searches for life as a planetary-scale chemical phenomenon, not for life as a technological phenomenon. The TRAPPIST-1 system, discovered in 2016 and characterized in detail in a 2017 Nature paper by Michael Guillon and colleagues, has become the focus of the most intensive biosignature search program currently underway. TRAPPIST-1 is an ultra-cool red dwarf star, approximately 39 light-years from Earth, around which 7 Earth-sized planets orbit in configurations so compact that all 7 would fit within the orbital radius of Mercury around the Sun. 3 of the 7, designated TRAPPIST-1e, Far, and Gay, orbit within the star's habitable zone, and their sizes and estimated densities are consistent with rocky compositions. The Webb telescope has already obtained transmission spectra of several TRAPPIST-1 planets, with early results showing that at least some lack thick hydrogen-dominated atmospheres, a necessary but not sufficient condition for Earth-like habitability. The full atmospheric characterization of the TRAPPIST-1 habitable zone planets will require dozens of transit observations accumulated over years, and the results will represent the first genuinely informative data on whether rocky planets in habitable zones around red dwarf stars maintain the atmospheric conditions that biosignature detection requires. Jason Wright at Penn State University has worked to expand the search beyond the radio and atmospheric domains through the concept of technosignatures, observable consequences of technology that might persist in the geological, astronomical, or electromagnetic record long after the civilization that produced them had ceased to exist or had changed beyond recognition. The concept includes not just radio transmissions, but also the waste heat that any energy-intensive technological civilization would radiate into space, detectable in the infrared spectrum of a star system. The spectroscopic signatures of industrial pollution in a planetary atmosphere, the geometric regularity of large-scale structures that no natural process would produce, and the modification of stellar light curves by large engineered structures intercepting a fraction of the stellar output. Wright's work has brought systematic rigor to what was previously a largely speculative domain, establishing the observational signatures that each class of technosignature would produce and the instrument capabilities required to detect them. The significance of the technosignature framework for this episode's central question is that it extends the range of evidence that could, in principle, tell us whether the universe's silence is real or merely a consequence of looking in the wrong places with the wrong instruments. The Great Filter, the term coined by the economist Robin Hanson in a 1998 essay, and subsequently developed by philosophers and scientists, including Nick Bostrom, names whatever process or processes account for the gap between the apparent abundance of potentially habitable worlds and the absence of detectable evidence for extraterrestrial civilizations. The filter might be behind us. The transition from non-living chemistry to the first self-replicating molecule might be so improbable that Earth is one of the only planets in the observable universe where it has occurred, meaning that the universe's silence is real and we are, effectively, alone. If the filter is behind us, the silence is explained, the future is open, and the development of technological civilization on Earth is one of the most unlikely events in the history of the universe. Alternatively, the filter might be ahead of us. The transition from microbial life to complex life might be common, but technological civilizations might routinely destroy themselves or become undetectable through processes. War, environmental collapse, technological accident, voluntary withdrawal from the electromagnetic spectrum that operate on timescales short compared to the galaxy's age. If the filter is ahead of us, the silence has a different implication. It means that every technological civilization that has preceded us has failed to persist, and that we are approaching the same transition they failed to survive. The implications of these two possibilities are asymmetric in a way that Bostrom, among others, has noted. Finding evidence of simple microbial life on Mars, or in the ocean of Europa or Enceladus, would be among the most significant scientific discoveries in human history. Confirmation that life had arisen independently in two separate locations in the same solar system, implying that life was widespread throughout the universe. But it would also push the Great Filter forward, away from the origin of life and toward the development of complexity, suggesting that the filter, whatever kills civilizations before they become detectable, lies somewhere between the microbial world we would have found on Mars and the technological world we currently inhabit. Bostrom has written, with a candor that is unusual in scientific discussions of this subject, that he hopes the search for life on Mars comes back empty. An empty Mars is consistent with the filter being behind us, with the origin of life being the rare event that explains the silence. A living Mars is evidence that the filter lies ahead. The search for biosignatures in TRAPPIST-1 atmospheres, the breakthrough LISTEN survey of the nearest million stars, the technosignature searches in archival astronomical data, the continued expansion of the confirmed exoplanet catalogue, the planned Europa Clipper surface investigations, and potential future landers. These are the current instruments of the investigation, and they are all, in different ways, attempts to constrain the location of the Great Filter by gathering data about how far life progresses in environments other than Earth. Each result, positive or negative, narrows the range of viable hypotheses. A positive detection of atmospheric biosignatures on a TRAPPIST-1 planet would establish that life had arisen independently at least twice, and probably many more times, in the galaxy. A confirmed detection of a radio signal from a distant star system would establish that technological civilization had developed elsewhere and had persisted long enough to be transmitting. A continued absence of any such detection, across progressively more sensitive and comprehensive searches, would progressively sharpen the constraint on how rare complex life must be. The cost of hearing the silence clearly is the patience required to search carefully enough that the silence is informative. Project Ozma's 150 hours of observation across 2 nearby stars was not sufficient to conclude that the galaxy was quiet. The Breakthrough Listen program's survey of the nearest million stars with instruments orders of magnitude more sensitive than Drake's 1960 receiver is closer to sufficient, but still covers only a tiny fraction of the relevant parameter space. The silence, so far, is real, but it is the silence of an incomplete search, a search that has covered, by some estimates, the equivalent of a glass of water drawn from the world's oceans and examined for fish. The absence of fish in the glass does not establish that the oceans are fishless. What it establishes is that the search must continue, and that each increment of coverage, each new telescope, each new detection technique, each new class of biosignature examined, moves the constraint forward by a small but real amount. What the universe's silence means, if it is silence, and the search is not yet complete enough to be certain, is that somewhere between the formation of worlds and the emergence of minds capable of detecting each other, most of the potential has been lost. The mechanisms of that loss are what this episode has moved through. The magnetic fields that fail and leave atmospheres unprotected. The runaway greenhouses that seal surfaces beneath acid clouds. The glaciations that nearly return living planets to dead ones. The impacts that reset biospheres accumulated over hundreds of millions of years. The slow failure of the specific conditions that allow complexity to accumulate across geological time. Most worlds that formed are silent now, not because they were never candidates, but because the chain of conditions required to move from candidate to complex is long, and each link in it can fail. The fade. There is a planet, 39 light-years from here, orbiting a dim red star in a period of just over 9 days, whose atmosphere the Webb telescope is currently examining one transit at a time. Each transit lasts roughly 36 minutes. Each observation accumulates a small increment of signal against the noise of the background light, and the accumulated signal will eventually, over years of observation, either show the presence of specific molecules or confirm their absence. What the telescope is looking for, specifically, is a chemical condition. Two gases present simultaneously in concentrations that no geological process sustains. Oxygen produced by one metabolic pathway, methane produced by another, the two reacting slowly in each other's presence, each disappearing on a timescale of thousands of years unless continuously renewed. Their coexistence in measurable quantities in a planetary atmosphere would mean that something was renewing them, something running a chemistry that the atmosphere alone, and the rock beneath it, and the star above it, could not maintain without assistance. Whether that chemistry is running on that planet, whether the signal, when enough transits have been accumulated, will show the disequilibrium or will show instead the flat, featureless spectrum of a world that has reached chemical equilibrium with itself, the spectrum of a place where nothing is running anymore, is not known. The telescope continues to observe. The transits continue to occur, each one lasting 36 minutes, separated by 9 days. The planet crossing the face of its star in a geometry that has been repeating since long before anyone was here to measure it. The signal accumulates slowly, in increments too small to interpret individually, building toward a threshold that will eventually tell us something about whether the silence of this particular world, at this particular distance, in this particular direction, is the silence of chemistry that never started, or chemistry that started and stopped, or chemistry that is, quietly and without any awareness of being observed, still going. The universe does not answer quickly. It has time. The journey is complete. Rest well.